Hey, Jeremy. Is my microphone working?
Hi, David. Yes, it's Adi here. It is working. Jeremy's also here. I don't know why he's not responding, but I see him here. But yes, your microphone is working. Thank you.
I hear it. I hear it as
Okay.
well.
Okay, great.
And you can try screen sharing if you want now, or we can do it later. It's up to you.
Hello?
Hi, David.
Looks,
Can you hear us?
Okay. Hi. Everything's working now?
Yeah, we hear you well. If you want to just try sharing your screen, you should have permission to do that now.
Okay, that's easier said than done, but let's try. Okay, how does that look?
Perfect. Perfect. Adi, do you have slides for your first little bit or not?
I'm just going to speak for a couple of minutes. I don't have any slides.
Okay. Okay. We'll just let David leave his slides up.
Okay, sounds good.
Actually, we'll just switch the screen back to the BTS screen, and then you can reshare after, David.
Okay, hope it'll work.
All right, we'll get started. So welcome everyone to BTS 2023. So this is our 5th edition of the BTS conference. I'm coming to you from Concordia University. Concordia is in Montreal, Quebec. I'd like to acknowledge that Concordia is located on unceded Indigenous territories of the Kanien'kehá:ka Nation. So today and tomorrow, this event was planned by myself and my co-chair, Adi Mashetan, who's at Toronto Metro University. And BTS is really her brainchild. So she made the original edition, which was at the Fields Institute in Toronto. And we've moved around since then across different cities in Toronto. So I'm going to turn the floor over to Adi to just maybe tell us a little bit about BTS, and then we'll get started with all the great talks that we have lined up today. So Adi, take it away.
Thank you so much, Jeremy. Thank you. You're very kind, my brainchild. Very, very, very exciting to be here, everybody. Let us start with also my acknowledgement, land acknowledgement. I'm calling from Toronto. Toronto comes from the Mohawk word te Kronto, meaning the place in the water where the trees are standing. Toronto is home to many Indigenous people from across the territorial land, and I'm grateful to have the privilege to work on this land. I'm Dr. Adi Mashetan from Toronto Metropolitan University, as Jeremy kindly pointed out. On behalf of the steering committee, because this is group effort, steering committee, Professor Ray Safavinaini of University of Calgary, Dr. Vicky Lemieux of University of British Columbia, and Dr. Jeremy Clark of Concordia University, I would like to extend a very warm welcome to each and every one of you joining us for this year's event, Blockchain Technology Symposium 2023, hosted virtually by Concordia University. Jeremy already mentioned this. It's a great pleasure, just to point that out again, that this is our 5th BTS. So this pan-Canadian forum started in 2018 at the Fields Institute. Of course, before the pandemic, it was in person, followed by BTS 2020, also in Toronto, and BTS 2021, hosted by University of British Columbia, and BTS 2022, hosted by University of Calgary. Our aim at BTS has always been to hold it annually as a forum where academic researchers, industry professionals, and policymakers, decision makers come together to present recent advancements in blockchain technology, discuss adoption barriers, tackle common challenges, and explore future roadmaps surrounding this very promising technology and its related technologies. Following this tradition, BTS 2023 has gathered a diverse group of prominent speakers from academia, industry, and policymakers to continue this very crucial dialogue. This year's event is free, virtual, and multidisciplinary with an exciting program with keynote speakers, prominent academics, David Zhao, Costas Kryptos, Jill Gunter, invited speakers, Peter Chow White, Joni Brennan of Digital ID and Authentication Council of Canada, Cyrus Minwala of Bank of Canada, Doug Heitzman of Blockchain Research Institute, and Patrick Mandic of Mavenit, as well as contributed talks from Canadian researchers from coast to coast to coast. I take this opportunity to sincerely thank all of the keynote speakers, invited speakers, and contributed talk presenters for their valuable contribution to BTS. BTS would not be successful in its 5th year without your generous knowledge sharing and contributions. I also want to thank the participants who join us year after year, whether on Zoom or on YouTube. This is being streamed live. This is us. This is the BTS community, and it's great to have you. And before I hand it back to Jeremy, I'd like to thank him for putting this program together. He did all the heavy lifting this year. And stay tuned for an announcement about where BTS 2024 is going to be next year. We are aiming for a larger event with some in-person and some online components. Thank you very much and enjoy BTS 2023. Over to you, Jeremy. Thank you.
Great, thanks. Thanks a lot, Addie. Okay, so with that, we'll just move into our first talk. So David, if you want to work on getting your screen shared again. So the first talk will be by David Zhao. He's a professor at the University of Waterloo, which is Addie and I's alma mater. He's also chief cryptographer at Evolution Q, and he's going to talk about some elliptic curve moon math, as we like to call it, or isogenies with applications to blockchain. So take it away, David. Thanks.
Okay. Is my voice coming through?
Yeah, everything sounds great. We can see your.
Do I have video? Like, can you see my face?
I don't see your face, but now I see your face.
Okay, so video, voice, slides, everything's fine?
Yeah, perfect.
Okay, so I should just start?
Yeah, go ahead.
Okay, so in keeping with the territorial acknowledgements that we've had so far, I'd like to acknowledge on behalf of the University of Waterloo. So the University of Waterloo acknowledges that much of our work takes place on the traditional territory of the neutral Anishinaabe and Haudenosaunee peoples. Our main campus is situated on the Haldimand Tract, the land granted to the Six Nations, that includes 6 miles on each side of the Grand River. And our active work towards reconciliation takes place across our campuses through research, learning, teaching, and community building, and is coordinated within the Office of Indigenous Relations. So thank you so much. So I'm going to talk about some applications of isogenies to blockchains because isogeny-based cryptography is my research area and blockchains seems to be the topic of this conference. And so when you put them together, that's what you're going to get. Now, maybe some of us might need a little refresher on like what isogenies are and what elliptic curves are. So I'll do that to start out. So elliptic curves are used in, I think, most blockchains. They're the most practical option for a lot of operations that you simply need to have on a blockchain. These are defined as sort of mathematical objects that are given by these cubic equations, with a degree 2 in y, degree 3 in x. And the cool thing about elliptic curves for our purposes is that they form a group. So if you take a bunch of points here, like let's say, so we have 1 point over here P, and we have 1 point Q, and you want to add them, then you draw lines and you reflect the lines around the x-axis or something like that, and you get the sum of the points. And you can take this sort of mathematical operation and you can form a group out of these points lying on the curve. And this group is really useful for cryptography. It lets you do lots of things. It lets, things like, ECDSA, which is used in Bitcoin, are, instantiated on the group of points of an elliptic curve. Now, what we're going to talk about is we're going to talk about a sort of more complicated object that you can impose on elliptic curves. And that's very simply the maps between elliptic curves. So when you have any sort of object in mathematics, you should always think about what the maps between the objects are, right? So like groups and group homomorphisms or vector spaces and linear transformations. And so when you take an elliptic curve, the object that you want, these sort of concept that you want when you want to talk about functions or maps between elliptic curves is this concept of an isogeny. So an isogeny has to preserve sort of the two main mathematical structures that we recognize on an elliptic curve, which is, first of all, that they're curves, they're algebraic curves, they're defined by polynomials. And second of all, they have this group structure. They're sort of group sets with an operation that forms a group. And so if you want to map between groups, then that would certainly have to be a group homomorphism. And if you want to map between algebraic curves, if you want to map between sets of points defined by polynomials, then what you're looking for is a polynomial map, right? Or actually, more generally, you can allow a rational map. So a rational map is just a quotient of polynomials. Okay, so putting those together, we get the definition of an isogeny. It's just a map between two elliptic curves, which is both an algebraic map, so that it's a rational map, it's a quotient of polynomials, and also it's a group homomorphism, so that it preserves the group structure. Okay, and it's a little bit, it's easy, I think, to lose sight of what these objects really look like. Elliptic curves, as we recall from this previous slide, they're sets of points in the plane, right? So like every point on the elliptic curve has an x coordinate and a y coordinate, and has 2 coordinates. And so when we talk about rational functions, we mean rational functions in two coordinates. So that means two inputs and two outputs. And so it becomes a little bit cumbersome to deal with all the notation. But if you just remember that there's two inputs and two outputs, then everything else sort of follows from that. Okay, so you take quotients of polynomials, and if your quotient of polynomials maps one curve to the other, and it's a group homomorphism, then we say it's an isogeny. Just to give you some examples of isogeny so that you know kind of what they look like. So with an elliptic curve, we can consider, so when we consider maps between elliptic curves, like something like, a map from E to E prime or something like that, being a group homomorphism, like if you think of just a regular group homomorphism, hopefully you've taken some abstract algebra or linear algebra at least, right? Whenever you have a map between algebraic objects, you can take the sort of what we in linear algebra we call the null space, or in abstract algebra we call it the kernel. You can take the set of sort of points that get mapped to zero or that get mapped to the identity. And this is a very sort of important way to characterize what maps look like. In fact, you learn in algebra or linear algebra that for the most part, these maps are actually defined by their kernel. If you know what goes to zero, then you pretty much know where everything else goes up to isomorphism or something like that, right? So in this case, and in most of our cases, what we can do is we can interchangeably think of maps and their kernels as being the same object, that a kernel gives you a map and a map gives you a kernel. So if we specify a map by saying what its kernel is, that actually does, in a certain sense, describe the map completely. Right. So suppose in this case, I want an isogeny of degree 2. Okay. So what I mean here is that, there's going to be 2's all over these. The degrees of these polynomials are going to be 2. Right. Then we know from just high school algebra that a polynomial of degree 2 has 2 roots. Right. There are sort of, in a certain sense, there's 2 points in its kernel. That's more or less what it means for a polynomial to have degree 2. So here, if we take a kernel and we take it to have size 2, and we take the isogeny corresponding to that kernel, which is the isogeny that has that kernel, or an isogeny that has that kernel, then we can expect to get an isogeny of degree 2. And that's exactly what happens here. Now we have to be a little bit careful when we take a kernel of size 2, because unlike high school, you can't just take any old 2 points and set them to be the roots of your polynomial. You have to be careful about it because you need a group homomorphism, right? And so what that means is the kernel has to be sort of closed under addition, that if I add 2 points in the kernel, I get another point in the kernel. And so in particular, if I add the non-identity point, I have to get the identity point. 1 + 1 is 0. There's no sort of other way around this when you're in a group of order 2. Right. And then from the theory of elliptic curves, you know that if a point plus itself is the identity point on the curve, then that point must lie on the x-axis. It must have a y-coordinate of 0. Okay. So now the y-coordinate is 0. The x-coordinate is, well, whatever, but it's going to have to satisfy this equation. Right. And then you take that x-coordinate and whatever that is for that point. Now that's a fixed x-coordinate for this point. That's going to go into your various values here. And then the x and the y, these are your variables, right? So these are it's a function after all. So you have input variables. So the x and the y without subscripts, those are your input variables. The x and the y with the p subscript, those are the constants coming from the kernel point. Okay. So that's an example of an isogeny of degree 2. You can do similar examples. You can look at an isogeny of degree 3. Again, that means that your kernel has to have size 3. So you have to have 3 points in the kernel. And since you're working in a group, these points, they have to satisfy certain algebraic relationships. So they have to be of the form, P minus P and the identity point. Okay. And so now P is going to have this form. I didn't write down minus P, but minus P actually has sort of almost the same coordinates. It's just that the y coordinate is negated. And then you take these values, xp and yp, and you're going to insert them into the appropriate places in this formula. Okay. And then you can get sort of a corresponding isogeny of degree 3. And you can actually do this for any particular size of kernel that you want. You can literally just write down the kernel, what it's going to be, and then you can write down the equations for what the elliptic curve is going to be and what the isogeny is going to be. So here, this isogeny, my notation here is that here's the E, here's the E prime, here's the phi, and phi is a map from E to E prime. Right? So that's what one of these things looks like. It's too difficult, I think, to write this down off the top of your head. But once you see it, I hope you recognize that these are not actually that scary an object. They're just rational maps, right? They're rational maps of a particular form. If you want an interesting algebraic exercise, you can verify that these coordinates satisfy this equation, which they do, because the isogeny has to map E to E prime. But yeah, okay. So that's what they look like. Those are just some examples. The key takeaway from these examples that I want you to get is that as the degree gets larger, the isogeny gets more complicated. So there's going to be sort of more and more terms as we increase the degree. So we can't just increase the degree, without restriction. What's going to happen eventually is that the rational functions are going to become too complicated to write down or evaluate, right? So the whole sort of trick in using isogenies in any sort of computational setting is you have to keep that degree under control, so that you can actually compute the isogenies. You want to be able to compute with these in order to, do blockchains or cryptography or any sort of computation. Okay, so I'll start with describing a scheme that I submitted along with a team to the NIST post-quantum standardization process. This scheme is called SIKE, Supersingular Isogeny Key Encapsulation, as you can see from the title here. You may have heard SIKE is broken. SIKE has gotten broken. So this scheme was broken, although not until it reached round 4. So it took a while. It took 10 years to be broken. It has been broken. The break was published by Kastrick and DeCreux in 2022. So just around the time that SIKE was announced as a candidate in round 4 of the NIST process, the attack was published. So don't actually use SIKE. It's not secure. It's now that we know how to break it, it's it can be broken in a matter of seconds on a computer. But I'm going through this just to sort of explain for you, an example of an isogeny scheme and how we think about these kernels and use them in some sort of cryptographic setting. And then later I'll talk about some actual unbroken schemes that we can use. Okay. So SIKE is based on this primitive that DeFeo and I invented in 2011 called supersingular isogeny Diffie-Hellman. And the way that this works is, again, so we remember that we think of isogenies and their kernels as being interchangeable. So I'll just sort of circle the kernel here and the isogeny down here. All right. And so that kernel and that isogeny, they in some sense represent the same thing. And then similarly with Bob's, so you have a kernel here and an isogeny here, and each one is the other. They're written down differently, but they mean the same data. Okay. And so what Alice is going to do in this SIDH scheme is Alice will pick a kernel and compute the corresponding isogeny. And then the isogeny is going to be the secret in the scheme. And then what's going to be published is the destination of the isogeny, sort of the place where the isogeny maps to. And so in this case, that destination is what I call this quotient group E modulo A. All right. And Bob is going to publish the same thing with a different private kernel. So that's going to be E modulo B. The shared secret is going to be E modulo both A and B. And the way that you can do that is you can take E modulo A and then you can mod out by B, or you can take E mod B and you can mod out by A. Okay. And so that's going to give you the same thing no matter which way you do it. In both cases, you're just sort of saying that both A and B lie in your new kernel. The one subtlety here, which at the time led to a sort of clever workaround, but nowadays we know and ended up being the sort of key weakness that allowed SIKE to be broken. So the problem here is that when you want to take E mod A and mod out by B, you can't literally do that, right? Because B does not lie inside E modulo A. Like B isn't over here, right? B is over here, right? B is a subgroup of E, right? A kernel has to be a subgroup of the original group that you started with. And so here, since B is a subgroup of E, you can't actually compute E mod A mod B. Even if you know E mod A and you know B, you can't just mod out E mod A by B because B doesn't lie in the right place. It doesn't sit in the right place. You could, of course, take B and transport it through phi of A, but phi of A is the other person's secret. And so to get around this problem, what DeFeo and I decided to do was we decided to have each of these groups sort of living inside a larger group. All right, so it doesn't really matter what this larger group is. If you recognize what it is, then great. But each of these groups sits inside a larger group. And then what you do as part of the key exchange is that each person describes what their isogeny does to the other person's larger group. Okay, you can't just say, oh, this is what my isogeny does to your kernel, because your kernel is supposed to be your secret. There's no way to exchange that information. But you can say, oh, here's what my isogeny does to this big group that contains your kernel. I don't care what your kernel is. It's inside this big group. Here's what my isogeny does to all of these points. And so now you can go figure out what it does to your kernel. All right. And so that's, great trick. The problem is that it's this extra information here that ended up being the reason why Psych was broken. And I think we understand that, now that giving away your sort of isogenies, effects on some big subgroup, even if it's not the subgroup containing your kernel, is not going to end well. That it's going to result in your isogeny being compromised. Okay, but that's the whole trick, right? Is that when you publish this extra information, then the scheme becomes insecure. But we still believe that when you don't publish this information at all, then we're back to this, what we still believe is a hard problem. Given two curves, find an isogeny between them, right? So that's the sort of underlying hard problem here. Now, there's a lot, and I mentioned this and I want to sort of emphasize this because a lot of people working in cryptography, I think, are under the impression that isogenies are insecure, right? They've been broken. The NIST process only had one isogeny candidate, which was Psych. Surely that must have been the best example of an isogeny-based system, and that scheme was broken. And so if that one's broken, then we can't trust any of the other isogeny schemes. They're still too new, right? Well, while I would agree with the assertion that isogenies are perhaps very new and still need some time to build up extra trust, I don't sort of agree with the general principle that, oh, because Psych is broken, then all the other stuff is broken too. Right? I think that there's, in my view, and in the view of, I think, most people who actively do research in this area, there's a sort of real meaningful difference between this kind of situation where you publish this extra information and the generic isogeny problem where you do not publish that information. All right. And I do want to highlight, there's this wonderful webpage created by Luc DeFeo. It's called Is Psych Broken Yet? Well, the answer for Psych is yes. But the answer for all these other isogeny schemes is more complicated. Some of them have been broken, some of them have not. Okay, and so there's a great summary of everything over here that you can always refer to if you want to learn the current state of the art of attacks with respect to any particular isogeny crypto system. Okay, so now we'll go on and we'll look at some still unbroken schemes. All right, so some other, oops, sorry, I'm going to have to get up and wave my hands for a moment because room lights just went out. It's a wonderful room with all sorts of amenities like a mini kitchen and a rock climbing wall, but it does have automatic lights that need to be motion sensor triggered every now and then. All right, so the sort of spiritual successor to Psych might be this Seaside protocol. Seaside, well, I couldn't fit it in the title, but it stands for commutative SIDH. Okay, and it was invented by 5 authors: Castor, Blanc, Martin, Dalpani, and Rennes. And Seaside is a sort of alternative key exchange based on isogenies, which does not exchange any extra information about the isogeny. So it only, in C-side, you only give away the endpoints of the function, the endpoints of the isogeny, and the hard problem is to find the isogeny. Okay. So C-side itself is based on sort of an earlier version of the same protocol invented by Kuvenius in 96 and Rostovtsev and Stolbinov independently in 2006. That scheme is these days called CRS to distinguish it from C-side. The difference between C-side and CRS is that C-side also borrows some ideas from psych or SIDH, right? So in C-side, just like in psych, you use a supersingular elliptic curve. And the reason why you need a supersingular elliptic curve in psych is specifically because if you want kernels of these sizes, 2 to the E and 3 to the F, if you want to be able to control the size of the kernel, then you need enough curves out there for you to do that. And so far, only supersingular curves give you enough curves. Sort of the density of isogenies among supersingular curves is, I think it's like an asymptotic order larger than the density of isogenies over non-supersingular curves. Like, for example, supersingular curves are expanders that satisfy the Ramanujan bound, and non-supersingular curves that are still expanders, but they don't satisfy the Ramanujan bound. So if you want to have sort of enough isogenies that you can pick and choose which degrees you want, which ends up being, a matter of picking and choosing the prime that you sort of want to use. In this case, you would use a prime like this, right? Then you need to take a supersingular curve. Otherwise, there's no real reason why you need to take supersingular curves. Okay? But in C-side, you also want to be able to control sort of what these isogenies have as their degrees. So in C-side, you would pick a prime which is sort of a similar sort of structure to psych. It looks like something like this, something like that, where eventually you have some prime like that, and then -1. Right? So it's the same kind of prime, and then you're going to take a supersingular curve over that kind of prime. So I think that idea was borrowed from psych, but the rest of it, everything over here, was borrowed from CRS. Okay, all the rest of it looks just like CRS. So in CRS or C-side, what you do is your keys or your kernels are going to be subgroups of a special form. And so these subgroups are derived from what we call ideals in the ideal class group. So you're going to take the ideal class group of the endomorphism ring, or in this case, the sort of FP endomorphism ring, hence the P in the subscript over there. You'll take the class group of the endomorphism ring, you'll take an ideal inside there, or more specifically an ideal class. That's the CL means ideal classes. Right, so these are equivalence classes of ideals. And then you're going to sort of derive a kernel from that ideal. So that kernel is derived like this, right? Now here I've written it as an ideal. In reality, you have to check that this sort of result ends up being independent of the, which ideal you pick in the ideal class. And actually this result, this subgroup does depend on the choice of ideal. But what doesn't depend on the choice of ideal is sort of the up to isomorphism, the curve that you end up on does not depend on the choice of ideal. Okay, so that part works out fine. And then Bob does the same thing. Bob picks an ideal inside this endomorphism ring and then computes this kernel derived from the ideal. And the sort of nice mathematical property that makes CRS or C-side work is that this operation where you derive a kernel from an ideal ends up being a group action where the group is the ideal class group. So this is the class group of the endomorphism ring. Okay. So because it ends up being a group action, you get a very sort of nice Diffie-Hellman looking like protocol, which the authors called C-side. Okay. All right. So that's sort of a quick introduction to isogenies and the current state of the art in encryption and key exchange. Now, for blockchain applications, we don't actually need encryption or key exchange. Blockchains are all about signatures and authentication. Okay, and so you might ask, well, what does all this have to do with blockchain? Why am I going over all this stuff? Well, it's pretty easy to describe. So we can sort of, if we look at a typical blockchain, so I think it's going to look something like, if I have the right page here, something like this, right? For Bitcoin, let's say, the structure of the Bitcoin blockchain, it consists of a bunch of transactions, right? And these transactions are chained together. And the way that you assign coins to somebody else is you were previously assigned coins from some other source, right? So you're going to get the coins, whether from mining or from, just somebody giving you some coins, right? So you have some coins in your wallet. And when you want to transfer those coins, let me make this figure bigger so I can draw on it. When you want to transfer those coins over to someone, what you're going to do is, so you start, let's say you're owner 0, right? So what you're going to do is you have these coins in this wallet, and when you want to do a transfer, what you're going to do is you're going to sort of plop your signature. So right here, your signature, you're going to plop your signature onto those coins inside a transaction block. And that transaction block is going to include somebody else's public key. And so that somebody else is the new owner of the coins. So when you want to transfer coins on your chain from you to somebody else, you're just going to take their public key, put it in a transaction. You're going to hash it together with the previous transaction block. And you're like there was a whole previous block here that was the transaction where you received the coins, right? You're going to take that, you're going to hash it in with the new owner's public key. You're going to sign that. And this signature scheme, crucially, is done using ECDSA. If only Satoshi Nakamoto had known about EDDSA, which wasn't invented yet, our lives would be much easier. But when was Bitcoin invented? 2009, I don't remember, something like that. ECDSA is what we have, right? Although he could have used BLS. I say he, Satoshi could be anybody. I don't know. I don't want to misgender Satoshi. But yeah, so Satoshi could have used BLS, but ECDSA is what we have. It's an elliptic curve, digital signature algorithm, and this particular algorithm sort of has some very nice properties. It has small keys and small signatures. I'll get to that in just a moment as to why that's so important, right? So your key goes in one transaction block, the signature goes in that same block. And now, as of like this moment, once this transaction gets published on the blockchain, now the coins no longer belong to owner 0; they now belong to owner 1, right? And how do we know who owner 1 is? Well, owner 1 is whoever owns that public key, right? And what owning that public key means is it means you can generate signatures against that public key, right? So then, when you want to spend those coins, then you would generate a signature, plop the new owner's public key in a new transaction block, and then that would sort of sign the coins over to owner 2, and so on and so on and so on. All right. So we identify owners by their keys. The ability to generate those signatures is what allows us to say that this entity owns those coins and no other entity does. Okay. All right. So why does this matter so much? Why do we why might we care about isogenies? Well, what if, so this is another sort of aspect of the research that I do here at Waterloo, and also with Evolution Q, our company, which specializes in sort of post-quantum security solutions, right? So the question here is going to be, what if somebody one day builds a quantum computer and breaks ECDSA, right? So we know that with a sufficiently large, reliable, and usable quantum computer, all of sort of discrete log-based cryptography, including elliptic curve cryptography, will be easily broken. It is going to fall, and we know how to do it. You just use Shor's algorithm, right? So as long as you can implement Shor's algorithm, you can break ECDSA. What sort of bad things would happen to Bitcoin if somebody built a quantum computer, right? Well, it looks pretty bad, right? Because what happens is, so now when you have a wallet, it's protected by it's identified by the public key, but it's protected by the private key, right? The private key is what lets you transfer the coins from that wallet to somebody. When everything is working properly, only the owner of the wallet should have the private keys. But if we have this sort of magical quantum computer that might exist one day, and there are sort of different stories as to when quantum computers will become a thing, with various people taking bets on the sort of NIST post-quantum standardization mailing list forum. So we don't actually know. People have been saying, oh, it's going to be 10 years or 20 years from now. They were saying that 10 or 20 years ago. So you maybe have to take some of these predictions with a grain of salt, right? But people are working on it, and there's no physical reason we know of why it can't happen, right? So if the quantum computers end up being built, then what's going to happen is that there's no sort of authentication security, right? So when we publish a public key, then anybody with an appropriate quantum computer can then just break that public key and get the private key. And so you'd have lots of sort of competing owners, right? You have lots of people saying, oh, I have the private key, I can sign over the wallet, and no, I have the private key, right? And so and the only reason why everybody has the private key is because everybody broke it using their magical quantum computers, right? So what can we do? Well, it turns out that, I mean, yes, people have already thought of this problem, right? So there is a thing that many Bitcoin implementations actually do right now as a countermeasure to largely mitigate the effects of let's say quantum attacks against elliptic curve DSA, ECDSA, or something like that. What they do is that instead of putting the new owner's public key in there, they're going to sort of hash the public key and put that in there instead, right? So all of these sort of transaction blocks, instead of containing an actual public key, you would first like pre-hash the public key and then hash that, right? So you would treat the hash of the public key as the public key, okay? And so that does address the problem, right? So now your public key isn't just floating in the blockchain, it's not there anymore. There's a hash of a public key, but hashes are supposed to be hard to invert, even with quantum computers. You can't just invert a hash, right? So you can't get at the public key because it's only sort of stored on the blockchain in this hashed form, and being hashed, since you don't have the public key, you can't then use your quantum computer to attack it to get the private key, okay? All right. So that seems to work, I guess. Well, it does, but when you transfer the coins, you still need to reveal your public key, right? Because in order for somebody to verify the signature, right? So, how do you verify? Let's say I wanted to verify that the signature was correct, right? That, this owner 2 actually meant to transfer the coins to owner 3. How do you verify that public key? That signature? Well, you need the public key. Right. So this public key, the actual public key, needs to be posted somewhere, like public key number 2, let's say, for owner 2. That actual public key needs to be published eventually, right, on the blockchain. It's just that you can delay the publication until you actually use the public key to sign something. Now, okay, so that's great, but does that really solve the problem, right? The answer is, well, it doesn't completely solve the problem, as you might expect. There's still going to be some problems. So here's this analysis by Deloitte, which sort of lists does a sort of blockchain search to figure out what like proportion of public keys are vulnerable to quantum computers breaking ECDSA, right? So what do we mean by vulnerable? Like what kinds of things could go wrong given that we're using this sort of hashed key solution, right? Well, one thing that could go wrong certainly is that you don't hash your key, right? You're still allowed to post your public key in the blockchain if you really want to, right? So here's a larger version of that picture so I can write on it. In particular, the original like Bitcoins, right? I want to say the 1 million Bitcoins. So there's this millions graph. 1 million Bitcoins is right here, okay? So this level right here, this is Satoshi Nakamoto's personal fortune in Bitcoin. It's like 1/21 of all the Bitcoin. It's worth about $26.8 billion at the moment. So if you have a quantum computer, this will be a great sort of target to set it on, because you could get pretty rich doing this. I think all of these public keys, because they were generated so early in the process, they were all generated like back in the early days of Bitcoin. these don't use this new trick of hashing the keys, right? All of these coins are just sitting out there, guarded by a sort of an actually public key, which is that's the whole point. They're supposed to be public, but in this case, they actually are public. And so the public key is out there for anybody to break, right? And there's various other situations where you could end up with coins that have public keys. If you partially spend a wallet of some coins, but not all the coins, and then don't transfer the remaining balance into a new wallet, then you could end up with some partial exposure. So these kinds of situations. So Deloitte did this analysis. They found that right now about 1/4, which is like, I guess, this height relative to this height. Right now, about 1/4 of all the Bitcoin out there is stored in quantum vulnerable wallets, right? So wallets where the public key is public and just there for the taking if anybody builds a quantum computer. And just for reference, there's a hard cap on the total number of Bitcoin that will ever exist. That's around 21 million. So that's up here at this line. So eventually, that's where the sort of the green line is going to trend to. Okay. All right. So that's one thing, right? That, there's just some keys that are vulnerable, and there's just some wallets that are vulnerable. And you could say, well, so I'm a regular Bitcoin user. I'm not Satoshi Nakamoto. I use modern implementations. I'm very safe about this. I always transfer unspent balances to new wallets, which, by the way, most wallets that you download today, they will do that for you automatically. They'll sort of keep track of these keys for you, so you don't have to do that, right? So I'm perfectly safe, right? I don't need to worry about it. Well, no, not really, because you still have, there's still a problem, right? Like, so that problem is going to be, mining, right? So when we mine, there's something that happens here, right? That you have to pay attention to. So let's look at how mining works. Okay, so I'll just make this diagram a little bigger so I can tell you. So mining is this process where, so the way it works in Bitcoin, I'm only talking about Bitcoin right now. There's other things that you could talk about. We could talk about Ethereum, smart contracts, all of those. But for now, I'm just sort of keeping it simple with the basic sort of concepts, right? So in Bitcoin, what you have is sort of every approximately 10 minutes on average, a new block is mined, and that's an average. So it can vary. It can be 5 minutes, 1 minute, 60 minutes, whatever. But the difficulty is calibrated and recalibrated at intervals. That on average, this takes place every 10 minutes. Every 10 minutes, what happens is some lucky miner puts together a sort of block of a whole bunch of transactions in a hash tree, hashes them into some root hash, puts that root hash inside a block, chooses a nonce, which is like a 32-bit number, and then puts it all together in such a way that sort of the hash of this entire block sort of has this sort of magic value, which starts with a bunch of zeros, right? And the more zeros you've get it to start with, the sort of greater the difficulty you were able to surmount, right? And you can't just do this. There's no way to do this except by brute force, as far as we know, because hash functions are hard to invert, right? You can't just start with the prefix of zeros and then invert it. You have to just do a bunch of computation to this. So this is the famous sort of proof of work sort of mining idea that Bitcoin uses to validate coins, validate transactions on the blockchain. Okay. All right. So because this process is not instantaneous, it takes a good 10 minutes to do something like this, right? So now what's going to happen is that when you transfer coins, when you do a transaction, you say, oh, here's the coins from my wallet, I'm giving them to somebody else. Now you're going to publish your transaction. Let's say it's right here. It's this one right here. I've circled it right here, right? So when you do that transfer, now you want to stick it in the blockchain and you want to get it validated, right? And you want to take that transaction and stick it on the Bitcoin blockchain in posterity, so that anybody and everybody in the future is going to have that for reference. The problem, I guess, here is that 10-minute delay. You have to publish the transaction, and then only 10 minutes later does it get validated in the new block. Okay? And if you now have a quantum computer which is so strong and fast that it can break ECDSA in 10 minutes, well, then you have a real problem, right? So even if you take all the precautions, you have, modern day wallets that hash your keys for you, don't publish the public keys. Inevitably, the public key is going to have to be published when you publish the transaction. And once you publish the transaction, there's still this time delay between when you publish it and when it gets validated. During that time delay, somebody can swoop in with your public key, which they also have if they have a fast enough quantum computer, and then they can transfer the coins somewhere else. They can say, oh, no, don't give them to owner 2, give them to somebody else, right? And this is also the reason why we still need public key cryptography. You cannot make an entirely like hash-based, blockchain. You just can't authenticate without some sort of concept of public key authentication. You need that in order to make this scheme, this idea work. Okay, so now when we're worrying about this kind of problem, well, then now you really have to just bite the bullet and say, well, we can't use ECDSA in a sort of post-quantum world, right? Not when 10 minutes is, even if when 10 minutes becomes enough for somebody to break ECDSA, then we're going to have to move on to something else. Okay. All right. So then the question now is, well, what other thing could that be, right? Well, the natural choice would be to look at a post-quantum signature. Okay. So we have, a bunch of candidates for post-quantum signatures. There's this NIST standardization process that I've been talking about all this time, right? And the process recently reached a first conclusion, I think somewhere around 6 months ago, where we now have some idea of what our next digital signature schemes are going to be in a post-quantum world, right? And so there's this wonderful table here by Cloudflare that I'm going to reproduce here. I've shuffled the rows around a little bit, but it's essentially the same table here, right? So here's our post-quantum signature gallery. This is what we have to work with, okay? And on the top, we have these so-called non-post-quantum schemes, right? So these are what we use today, right? Well, more specifically, what we use today is something like, this top row over here, okay? So that would be 64-byte public keys and 64-byte signatures. Now, these figures are for NIST P256, which is not actually the curve that Bitcoin uses. Bitcoin uses, I think it's SecP 256K1, if I'm not mistaken, right? Something like that, right? It's not exactly the P256. Again, if Satoshi knew a little bit more about elliptic curve cryptography, Satoshi might have chosen like curve 25519 instead, but this is what we have, all right? So we have this curve, and it has 64-byte keys, 64-byte signatures. I'm off by 1. I think Bitcoin actually uses 65 bytes because it uses 1 byte for its own purposes. But if we look over at these transactions and how they're structured, right, you notice that the key and the signature, the key is over here, the signature is over here. They have to go inside each transaction block, right? Each transaction is going to have to contain a raw copy of the key, a raw copy of the signature. Right? And that's a lot of bytes. I mean, it's not a lot of bytes for one transaction, but on the scale of Bitcoin, it is a lot of bytes, right? So if we're talking about something like, 64 bytes for a key is for a signature, which by the way is pretty good. Notice that, there's nothing else, in the post-quantum land or even in the pre-quantum land that compares to elliptic curve cryptography, which is why Bitcoin uses it. Okay. But if we look at the collection of all the transactions as a whole, that's where it starts to get a little bit hairy, right? So we can just look it up right now. What are we looking at for not right now. This is like 1 day out of date, but whatever. As of yesterday, the total size of the Bitcoin blockchain was, what is this? 0.5 terabyte, roughly, something like that, right? So it's not that bad considering that this is the entire ledger of all Bitcoin transactions that have ever taken place on the blockchain, right? For something that's been going for this horizontal axis is wrong, for something that's going on for over a decade, to have it all in 0.5 terabyte is not bad, right? That could fit on my laptop, right? It's something that we could use. Okay, but now if we think about this in context, right? If we're talking about something like post-quantum cryptography, what would we have here? We'd have to use something, well, probably, let's say ideally we'd want to use something from these sort of middle rows, right? One of the NIST standards. What would that look like? Well, let's take dilithium, which is the sort of candidate that the sort of standardized signature scheme that NIST recommends for most applications, right? So now instead of 64 plus 64, which is 128 bytes, right, for a transaction block, a transaction block would now have to contain a public key and a signature, which is 1.3 and 2.4 kilobytes respectively. So we're looking at, I don't know, 3.6 kilobytes, give or take, right? What is that? It's more than 10, it's like 30 times bigger, right? I don't know if I have my math right, something like that, right? So instead of half a terabyte, it's 30 times bigger. So that's going to be a cool 15 terabytes if we were to do, blockchains with the NIST recommended, mind you. So the actual recommendation that NIST has, like most people should use this, right? So if Bitcoin were to use this, say hello to 15 terabyte blockchains, that would not fit on my laptop, right? You need a beefy server to deal with that, and it's not ideal, right? Ideally you want you want this to be a blockchain for the people, right? That anybody can validate the entire chain, starting from the Genesis block all the way over to what we have now, right? Well, we'd like to do better than that, right? We'd like to not blow up our blockchain by a factor of 30. Okay, fine. Okay, so what else can we do? Well, there's Falcon, which is an approved NIST standard. It's one of the candidates that made it out of the process and is on its way to standardization, right? So we could use Falcon, although I think there's still some debate as to whether or not Falcon 512 specifically is going to be included as a standard. There's some people, I think, who are saying that 512 might be a little too weak, that we might need to go up to the next sort of security level. But if we use 512, then we're looking at 1,500 bytes, and so, well, instead of 15 terabytes, this might only be 7 or 8 terabytes or something like that, right? But some of these other options on the bottom here are starting to look fairly attractive, right? Like, what about XMSS, with XMSS with Shake or with SHA-2 or whatever, it doesn't really matter. But what about XMSS, right? That looks pretty good, right? 32 bytes for a public key, 900 bytes for a signature. Can we just use that? I've actually seen some proposals, for a post-quantum blockchain, and the ones that I've seen all use XMSS, because it has, indeed, quite small, public keys and small-ish signatures, right? You could work with that. So what is XMSS? I don't actually know what it stands for, but I know what it is. It's a sort of, it's one of these hash tree based signatures, like stateful signatures, where you can only sign a certain number of messages before you have to rekey everything. So in this case, the 20 here tells you that this particular scheme can sign 2 to the 20 messages before you have to redo everything. 2 to the 20 is like, it's like 1 million messages. Okay. Now I'm actually when I look at this, I actually think, well, why do we even need 2 to the 20 messages? Why can't we just use one-time signatures, right? Because if we're going to follow sort of this practice that many modern implementations adhere to, which is every time you transfer money, you transfer all of the remaining balance out, right? So that you only need one signature, right? Then you're not going to need 2 to the 20 signatures, right? But I can see why you would want some sort of wiggle room, right? Because if you literally use a one-time signature scheme, then what that means is that if you mess up and use it twice, you're dead, right? So you'd be better off building yourself some safety margin. 2 to the 20 sounds as good as any. It actually doesn't affect the complexity too much, whether you have, a safety margin of 2 to the 1 or 2 to the 20. It ends up, adding only a little bit of overhead to the whole thing, right? But even so, it's a one-time, it's a limited time signature scheme. It can only sign a certain number of times, right? What if we don't want to make that adjustment? What if we just want to use signature schemes as we used them before, without too much change, but we'd still like post-quantum security, and we don't want to blow up the size of the blockchain too much. Well, then looking at this table, there's really only one option. So that's right here, right? So this scheme called SkiSign, which I'm going to talk about next, or I'll get around to talking about it eventually, right? So this scheme, it is isogeny based, and the I stands for isogenies, and it has really small keys and signatures in the post-quantum space, right? So relative to our other alternatives, if you want something with post-quantum security, and you still trust isogenies, which I've already sort of talked about, then that's what you want to do. Okay. All right. So let's go. So isogeny-based signature schemes. What do these look like? So just to sort of start out this discussion, I'll start by talking about signature schemes based on the key exchange protocols that we've already discussed, just because it's a little bit easier to understand the framework when you have some sort of place that you can start with as a reference. Okay, so let's consider SIDH signatures. You've heard SIDH and SIG have been broken, right? But actually, you can still do SIDH signatures. They're still not broken, right? SIDH signatures are still viable as far as we know, and the reason is that when you're doing signatures, you don't need to transmit that extra information. You end up not needing this at all, right? Well, I mean, you probably do want to sort of give it over here, but you don't need to like compute that, is what I'm saying. You don't need to compute that from partial information, right? You're just given that as part of the signature scheme. So the way that SIDH signatures will work is you're going to publish as your public key. You're going to publish sort of the items that you would publish in an SIDH key, except for the extra information. So just the endpoints of the isogeny. Okay, and it's a proof of knowledge, right? That's how all of these signatures are going to work. You're trying to prove that you know something. Okay, so how does that work in this case? How do I prove that I know the isogeny between E and E mod A? Well, I'm going to play the role of Bob, and I'm going to commit sort of as part of my signature scheme. I'm going to, as part of publishing a signature, I'm going to commit to Bob's curve E mod B. Okay. And then once I give that commitment, this is an interactive proof of knowledge. So that means I'm going to commit to something, and then I have you say, what would you like to challenge me on? How can I prove to you that all of this information is legit? And in this case, there's sort of three things. There's 1, 2, and 3. Okay, so there's 3 things that you could ask for. You asking for all 3, or even 2 out of the 3 would be bad, because then it would reveal the whole square. But if you ask for one of them, I can safely give you one of them without compromising my secret data, right? So let's say you say 2, well, then I'll give you phi 2. Let's say you say 3, then I'll give you phi 3. Not both at once. So you get to choose 1, 2, or 3, and then I'll give you phi 1, phi 2, or phi 3. Okay. And the idea here is that I can't trick you too often, right? Because if we do this a bunch of times, all with different commitments, then at the end of the day, if I manage to answer you correctly every time, probabilistically, you can be fairly convinced that I actually have the private information. Right. So that's how SIDH signatures work. With C-side, we have these schemes called C-sign or C-fish. The only difference between these two is efficiency. C-fish is more efficient than C-sign, but with some caveats that I'll talk about a little bit later. Right. So with C-side, the way that this works is we publish a public key just like before, right? So this is going to be a C-side public key. And I just want to prove that I know the private key, all right? And so I'm going to prove that by committing to sort of Bob's side of the key exchange, right? And then now the challenge, I don't need a square, I just need a triangle here. Now the challenge is going to be a bit. So if the bit is 0, then I'm going to do this. If the bit is 1, then I'm going to do this. Okay? So I'll give you sort of either this isogeny or this isogeny, not both at the same time. That would be insecure, but I just give you one. And so you can choose which one. But then at the end of the day, if I repeat this many times, you're convinced, you're completely convinced that sort of I know both of them, or I could know both of them because you were able to pick at will which one you wanted, and I was able to give you that one. Okay. So these schemes, because the challenge space is very small, it's either 1 out of 3 or 1 out of 2 or something like that. Because these challenge spaces are so small, you end up having to repeat this many times before you can be confident in the security of the signature, before you be confident that I actually know the private key, and so that I've actually signed a message successfully. Okay. And with these technologies, or with these sort of schemes, the whole name of the game is trying to optimize sort of how many iterations you need and what you do within the iterations to sort of minimize key and signature sizes. Okay, so here's some optimizations that people have used for CSign and CFISH. So one optimization is, well, when you publish the commitments, which are part of your signature, right? So these things, these commitments right here, when you publish these commitments as part of your signature, you don't need to publish the values of those commitments. You would just publish a hash. That saves you size, right? Because a hash is smaller than the commitment itself. But why don't we need to publish the value? Well, it's because when I publish this response, the verifier, knowing this map or this map, it doesn't matter, either one, knowing these maps, the verifier can rederive what the commitment should have been, right? Because you're going to rederive the arrow, and that will give you the destination of the arrow. Right. So you don't even need to send the actual commitment. You can just hash the commitment and then let the verifier verify at the end that that hash was correct. You can send multiple challenges. This is actually a standard sort of practice in like the Fiat-Shamir heuristic. You're just going to do the same, challenge multiple times. But in this case, there's a sort of further optimization that you can make, which is that sort of you can, instead of doing these all sequentially, you can sort of do them, it's hard to explain, but you could do them all sort of at once, and then just, ask, allow the challenger to ask for one of them to be opened or something like that, right? And then that actually lets you sort of perform this verification a little bit more efficiently. You can exploit what we call twists, which is the fact that B star E and B inverse star E, or the inverse is in the group, these are actually related curves. They're twists of each other, if you know what that means. So once you know one, you know the other. And so that actually allows you to sort of implement simultaneous commitments. It saves you a factor of 2 in sort of sending simultaneous commitments, right? So with all of these optimizations, throwing them all together, it turns out that for CFISH, this is CFISH, CSign is a little bit worse. But so for CFISH, we can actually get sort of public keys and signatures on the order of a kilobyte, or half a kilobyte to a kilobyte, right? That's already pretty good. It's smaller than dilithium, for example. Now, there's a caveat here, which is that CFISH uses a 512-bit parameter set, which we're not sure, but we don't actually think that provides level 1 post-quantum security according to the NIST standards. And so we think we're going to have to raise that. And the problem with CFISH in particular is that if you make the 512 any bigger, then you can't actually instantiate the scheme because the scheme is not polynomial time. So this is a wonderful blog post by Lorenz Panny. I'll just sort of leave the reference here in case you want to look at it. Okay, so with CFISH, we can't really scale beyond 512. We could with CSign, but CSign is even slower than this. Just to give you an idea, I think CSign, the signing and verifying times are on the order of like minutes instead of seconds. Okay. All right, but SkiSign. Now, SkiSign to the rescue. So what is SkiSign? SkiSign is this sort of new sort of idea based on, so it's by DeFeo, Coyle, Leroux, Petit, and Wesolowski. It's based on using supersingular curves, but not with a class group action, but instead with this sort of quaternionic sort of action. So the Q here stands for quaternion. So this whole thing now takes place in a quaternionic endomorphism ring. The way it works is, so in principle, the sort of big picture looks just like what it did with the other isogeny-based schemes. You have an isogeny, you're going to publish the endpoints, and you're not going to publish the isogeny, and you want to prove that you know the isogeny. Okay, and so here I'm using the notation from this eSign paper. So tau is your secret isogeny, right? And you're going to commit, as usual, to some sort of E1, right? So you're just going to pick another isogeny, and you're going to commit to E1. Okay, But with SkiSci now, the challenge is not a bit or a number from a small set. The challenge is going to be an entire isogeny in and of itself, right? So now the challenger will say, oh, here's an isogeny. Can you do something with this? And your answer should be, well, yes, I can, right? Because what you can do is, if you know the red arrows and the challenger told you the blue arrow, so you now know the blue arrow, then you can compute from E2 all the way to EA. Okay, so you can compute one map going sort of around the square. You can compute from E2 all the way to EA or vice versa. And so now you know a map from EA to E2, right? And so now you just publish that map as your proof of knowledge, right? You had to know tau in order to go around the square, right? If you didn't know tau, you wouldn't be able to go around the square and get from E2 to EA. Well, now, of course, there's a trick here. It's not that easy, right? You can't just give away, you cannot set your response to be, whatever, I guess, what would it be? It would be phi hat, psi, and tau, or like psi hat. You can't just give the composition of your three isogenies as the response. That would be silly. It would reveal tau, right? You would be giving away all of these three isogenies. So what you have to do is, once you have one path from E2 to EA, which is this sort of, so this is original path from E2 to E1 to E to EA. So this is your original path. It goes by way of indeed phi hat, psi hat, and tau, right? Once you get this original path, you need to be able to sort of come up with a new path, which is an original path. It's a, did I get this backwards? Yeah, I got this backwards. So you need to be able to come up with some new path, which doesn't reveal any information about the original path that you used to construct the new path. Okay, and so this is the by now well-known KLPT algorithm, Coel, Lauder, Petit, and Tignol. The KLPT algorithm does exactly that. Given one path, it lets you construct a new path. There's some subtleties here. KLPT requires like going back to a known curve as a starting point. And so one of the sort of mathematical contributions of SkiSci was describing a way to construct a new path without a sort of common reference starting point. And so that's what they did. So with SkiSci, if you're optimizing for key size plus signature size within a given security level, you're going to get something like that. That's where the 64 and 204 byte values come from. Right now, the key generation signing and verification times, they're not great. They're, like as is usually the case with isogeny-based cryptography, the keys are really small, but the running times are quite slow relative to everything else. But that's going to be the subject of future work. I think I already saw like an ePrint article last week, sort of improving these times by about 10%. And so that's just surely the first of many articles to come. So there's a lot of research to be done. There's a lot of stuff that we can do. There's a lot of applications of blockchains, isogenies to blockchain. There's lots of work. This is very exciting. Psych is dead, but isogenies are not dead. I think there's very, very much that isogenies can contribute to the blockchain world. Okay, so I think I'll stop here. I'm almost out of time, and maybe we'll have time for some questions, or if not, then we'll have a small break.
Sure. Yeah, we still have about 5 minutes. So if anyone has questions, you can just drop it in the chat. Is probably the easiest way. And if it's really complicated and you want to unmute, just tell me that you have a question that you want to ask, and then I'll work on letting you do that. So I'll start off. First off, this was really interesting. It was a very cool talk. There are some people obviously that are worried about like quantum attacks, but usually they don't go through all the details and what the future world would look like. There's one topic that you kind of mentioned that I just will get your feedback on. So let's say that whatever, Bitcoin, Ethereum, we switch to some candidate, we don't know which one, post-quantum signature. It still requires people to like kind of move their assets from the old ECDSA to the new signature. And a bunch of people aren't going to do it. And let's say that like, this is like maybe a corner case or a niche case, but let's say that there is someone who has funds. It's in one of these like pay to key hash things. So it's secure for now, right? And then they wake up one day, but it's post-quantum and they decide, oh, I want to move it over. right?
Hmm.
So people are, or at least there's a thread on Ethereum research that's like about this. One idea that's floated is you could use some sort of zero knowledge proof that's post quantum, and you could basically prove knowledge of your private key given the hash of your public key without actually issuing the signature and having it front run and stolen like you mentioned. But anyways, do you have any feedback or ideas along those lines?
That's kind of interesting. I mean, I hadn't thought of that particular scenario where somebody wakes up one day in a post-quantum world. So let's see. I think that if I were to go about that, what I would just focus on is proving that you know the hash, right? Like that itself, in a world where the private key has no value over the public key, the entire sort of security that you're hanging your hat on in this case is there's only one person who can invert the hash, right? And that is the person who owns the public key, right? So some sort of zero knowledge proof of the pre-image of the hash, I guess, is what I want to say. And I mean, there's certainly ways to do that, but the whole question here is, how efficient is it going to be? Most zero knowledge proofs are, special purpose for a particular application. I don't know what hashes people use here, but let's say it's SHA-2. Like, I don't know any sort of special purpose SHA-2 pre-image proving protocol. You'd have to use a generic protocol, and that could be very slow. But hey, if it's something that you need 50 years from now, then that's what you have, and that's what you get.
Yeah. So that's actually a great observation, that you don't have to go all the way to proving the public key. You just can prove the pre-image. And then people are thinking generic, like Stark-based zero knowledge proofs, which are post-quantum. They'll take a while to do the proof, but then once the proof is done, then it's going to be succinct for everyone to verify it at least. So it's the user will have to spend some time, but not everyone else. Anyways, one other thing I'll just mention is, you mentioned that you can't do a blockchain with just hash functions. You need public key. There actually is a kind of crazy idea about doing it with just hash functions, but the compromise is that you have to do like a 2-round thing. So you sort of commit to what you want to do. It gets put in the blockchain, finalized, and then you kind of reveal things. So it uses these Guy Fawkes signatures. But anyways, I'll send you a paper. I want to get to some other people's questions.
Yeah. Well, I mean, sure, you could use like hash-based signatures as well. Like it is possible. It's just in concept, I think you need something like public key cryptography, if you want to call it 2-round hashing, whatever. Then
yeah. So it basically reduces to just using a hash-based signature.
Yeah.
Okay, so Addie wants you to go back to the Cloudflare table, and she's wondering why the SQI is red.
Ski sign. Why is the performance right? It's just slow, right? So if you compare, so signing was 2.5 seconds, right? And so if you take the ratio of signing time on ski sign to the signing time on ECDSA, that number is 60,000. That 2.5 seconds to whatever it is, 90 milliseconds for ECDSA. That's a ratio of 60,000, and that's a large ratio, as you can see, compared to the other elements in this table. Is it going to be practical? Well, I mean, depends on your application, right?
Okay, and then we'll just do one last question. So someone wants you to make a prediction between lattice-based signatures getting small versus isogeny-based signatures getting fast, which is the more likely.
Well, this one's easy. As long as isogenies aren't completely broken, like Psych was completely broken, but as long as like the general isogeny problem stands, I think it's inevitable that the smaller will win over the faster, right? Because what happens is that obviously lattices are always going to be faster than isogenies, right? Unless lattices are broken, right? We're not going to catch up in that sense. But what's going to happen is over time, you see the numbers, the key sizes, they're going to grow, right? Because as attacks get better, you have to grow your keys. You can't shrink your keys. But the signing and verification times, those are going to fall, right? And of course, their isogenies aren't going to catch up. But what could very well happen is that they could be small enough that you don't care about them, right? Like right now, lattices are look at those verification times, right? Lattices are faster than, elliptic curves or whatever, right? But at some point you just don't care, right? If it's, 3 milliseconds or 3 microseconds or 5 microseconds, it doesn't matter, right? So as long as the performance is fast enough, inevitably the key sizes are going to grow. And so the long-term advantage is always going to be with the smaller keys.
Perfect. Okay, well, thank you. We can't clap for you, but we can virtually clap for you. And so thank you very much for this presentation. All right, so we'll move on. So Peter, I made you co-host, so you should be able to get your screen sharing going. And if you want to test your mic.
Hi.
We hear you loud and clear.
Perfect. Thank you, Jeremy. David,
I'll introduce you, but if you want to just get your
okay, yeah, please go ahead. Sorry.
I mean, I won't give a big long introduction, but yeah.
There's not much to say. Not much to say, so go ahead.
Oh, I could go on, but I just keep it short. So Peter Chow White, he's at Simon Fraser University, a professor in communications studies, and then he also runs a lab which is called the Jenna Lab. So I'll turn it over to you, Peter. Thanks.
Thank you. Let me see if I can get the technology worked out here. I haven't presented over Zoom in a little while, which is kind of nice to say for once. Get rid of that slideshow. Presenter view. Okay, can we see just the slide? Yeah.
So we see your presenter view. So we see your
my presenter view.
Things like that.
Okay. So that's interesting.
Which is fine.
It's okay. I'll try this.
Everyone can read your comments.
One more time. Interview, Zoom, and there. How about that?
That's perfect. Exactly what.
Yeah. Okay. Wow. Success. I'll take it. I'll take the win. Okay. Thank you, Jeremy. Also, thank you, David, for that presentation. That was way above my pay grade, but extremely interesting. And I think one thing I like about this starting off with David and then moving to me is that there's a real interdisciplinarity about blockchain. There's also trans institutions about this. It's great to see people from policy, industry. This is a really important conversation for all of us to have. And as we build capacity and understanding and innovations in the Canadian context. So thank you, Jeremy and Addie, the co-organizers, for having me in. Also thank you to the other organizers, my colleague from UBC, Vicky, and also Ray. I really appreciate it. It's going to be very different. I'm talking about today about how value is driven within crypto. My work, I'm from the School of Communication, but I've also got positions in computing science and also at UBC in the Faculty of Medicine. My work takes me in many different areas and in industries and in different contexts, including policymaking and industry and across different types of disciplines. So I think about how different conversations are coming together and converging in order to create new innovations like blockchain. And today I want to focus on just a nugget of some of the larger research programs we have at the Gina Lab and talk about this thing called the meme and this piece of cultural content that biologist Richard Dawkins, writing in a book, The Selfish Gene in 1976, coined this term and called this an infectious gene-like bits of culture that spread through personal social networks. Really prescient in the early days of the internet where barely anybody was using it. He started to think about these personal, how culture moves through social networks and the cultural or media packages that people use in order to talk to each other and share their sense of who they are, where they're from, and how to navigate the world around them. Scholars didn't really know what to do about this for the next 20 years. And, my field has been studying, the impact of media and the internet for, well over 100 years. What's the media doing to us? What's the internet doing to us? We didn't know what to do with the memes back then until the internet, obviously. When the internet came, the adoption of memes skyrocketed and it replicated at rates that would make rabbits seem incredibly docile. These are jokes, they're commentary, they're sometimes political content, but mainly about sharing our experiences of being human in the human condition and certain events and in different contexts. These things are cultural content that crosses genres and media channels through derivative user-generated content. And so what that means is that, you know, I grew up in the 20th century, so I grew up learning how to watch television. The millennials, the Zeds, they've been growing up learning how to make television. And these memes are part of their ability to engage with each other as we all do, and use media and use different channels, social media channels, community media channels, et cetera, in order to make content. Now, I say derivative user-generated content because oftentimes this is using content that's made by legacy large, media companies. Normally media companies in the 20th century, if anybody touched their stuff, would sue them. But for some reason, they leave them alone. They don't see them as valuable. And we share these things through these digital networks. We share of our experiences, of course, of COVID, how we felt we looked like in 2019 versus moving from a better self in 2019 to a battered self in 2022. Obviously, I don't think I look like the very handsome gentleman on the left, but I often feel like the guy on the right, especially when I get up in the morning. We shared our experiences of this new thing that everybody started to do, is working remotely, and what are people's different perceptions of the same activity. And you can see here where this thing called working remotely doesn't have one definition or one image or one narrative about it. And that narrative has to do about positionality. Who's making the judgment, or who's describing what happens, and what we think about this thing looks like is different from different perspectives. Professors also use them to express their anxieties about teaching. Often when I'm teaching this course and I've got these, really deep theoretical readings about the mechanics and the theories of communication, my students are much more interested in memes and meme research. And then also we move into crypto is not immune to these things, and crypto is often, and blockchain is often talked about through memes, through people's experiences of engaging with blockchain, such as the NFT one on the left, but also sentiments about crypto and the people that engage in crypto as well. Sometimes these sentiments are negative, sometimes they're positive, but they're constantly in motion through things like memes. Before I get too deep into memes, I want to just touch base on one of this driving sort of system underneath this, which is culture, right? Because these are cultural products. It's cultural content, and culture it's a very deep subject. I can't do. I'm probably going to do a disservice to many of my colleagues, but I'm just going to start with this: is that culture is our social operating system. It drives our social norms, our beliefs, our customs, our values, and our experiences, which form the basis of human action. Culture, and the way that culture makes us think about the world and ourselves in the world, affects what we do in the world as well, and what we buy, and also what we value. It provides us with a repertoire of symbols, languages, rituals, and practices that serve as tools for helping us understand and navigate our social and physical environments. It helps us interpret our experiences and make sense of the world and the people around us. It also tells us what's valuable and what is not. Now, this isn't a fixed or absolute understanding. Culture changes over time. We are constantly updating this operating system. But the way that we update culture is through the process of meaning making. Now, a lot of folks, my colleagues in computing science and elsewhere, have been, working for years, and decades trying to understand, how text and how all this content that's been put up on the internet, whether it's people's purchases through Amazon, or whether it's what we posted on Twitter, or likes and engagement, on other platforms like Facebook, how these symbolic moves somehow connect to value or connect to different actions. And value is, how we make value is one of those actions. Now, there's very sophisticated models for doing these things, and new AI technologies are accelerating that process. But the one thing that communication does particularly well is that we focus on what the engine of how culture is negotiated, transformed, and maintained, and that's meaning making. Right? We need to make meaning. We need to make meaning out of the world in order to connect the symbolics and our understandings on the one hand, and our actions and how we make value on the other. It's a very important engine. So that's how culture is being negotiated over time and constantly changing. So the question is, where does this happen? Well, the media, our interpersonal networks, our media channels, And increasingly through the internet, especially these digital communication networks, is where we negotiate meaning constantly through our conversations, through our posts, through our likes, through the comment sections, and through, of course, media content. Traditionally, in the 20th century, the major institutions of meaning making that drove us tended to be news on the one hand, but also these other legacy media channels like film, television, etc. These were the campfires that we sat around to tell cultural stories about who we are. But in the last 20 years, social media and especially community media have been these spaces, especially in the blockchain space, have been really important for shaping the space, the directions or understandings of these new technologies, these new cryptocurrencies, for example, whether they're good things, whether they're bad things, whether they're valuable, whether they're not valuable. We negotiate these as we talk about them and make sense of them. When I talk about community media, what I mean about community media is things like Telegram, Reddit channels, and Discord. So memes are these small cultural packets, these gene-like things that Dawkins pointed out. Is that they're much more than just funny or annoying content. These are ways and channels and content packages where we share our sense of social norms, our cultural values, and our personal experiences through them. They are actually vehicles for creating meaning in our lives as we share these things. They've also become a common cultural internet language. And the interesting thing about memes is that they have no economic value. This is probably why major companies allow their content just to be used, constantly on the internet without interacting at all. It just doesn't impact their economic bottom line, they think. Memes you can't buy, you can't sell. No one owns a meme. They have social value because we use them every single day, but they have no economic value until Dogecoin. So Doge launched in 2013. As many on these chats know, I don't have to brief everybody on Doge, but there are some characteristics I want to point out. It's one that it launched in December 13, largely as a joke, as the first actual meme coin built on the Shiba Inu Doge, the dog. This was hated by the blockchain community, at least most of it anyways. It was a much maligned meme and an actual blockchain by the people who were trying to build a decentralized financial system who had very serious intentions about what was going on in terms of building blockchains. However, it built a very strong community amongst its advocates and its fans. So what was driving value or keeping it afloat was this community who were building their own meaning around this, not as a negative thing as the main blockchain and the Bitcoin maximalists were at the time, but they saw it as a positive thing. It could have a positive contribution to the blockchain space and to the world and to this decentralized financial system that was being built. And interestingly, while many of its peers failed or turned into zombie projects, over the 2010s, it stuck around through multiple halving cycles and bull runs. It was worth less than a penny for that time, but it still was there, and in the shallows of the CoinGecko and CoinMarketCap rankings. Until 2021. In 2021, adoption didn't fail the direction that everybody thought it would. It actually accelerated. It rocketed into the top 10, much to the disgust of crypto OGs. And I put myself in that camp. My students, I teach courses on blockchain at SFU, and part of the reason I love being in a group like this is because it's like I found my people. I've been teaching the blockchain at SFU for 7 years, and I'm still the only one that teaches blockchain courses in the university. And so my students always want to do a project on Doge, and I try and shame them into not doing it. It's a garbage project, doesn't mean anything. But when it accelerated into the top 10, that changed my thinking on it, and something was different. Now a meme, instead of being worthless or being worth less than a penny, all of a sudden this meme was worth dozens of pennies, and it was getting a lot of attention. It jumped in the top 10. Not only did it jump in the top 10, it stayed in the top 10, and it's still there. So this visual on the bottom right there, that was taken yesterday. So it didn't just jump into it because Elon Musk started talking about it and engaging in this meme culture. He's reflecting what's going on. He's driving what's going on. The big event, of course, was getting on Saturday Night Live and being in the mainstream media and talking about it. It was quite a fascinating type of event. Right. So traditional understandings, of value creation, they focus on economics traditionally. In blockchain and crypto, what I'm going to try to point out here and bring to our attention is that value is also driven by culture. Okay. And we negotiate the value of coins through meaning-making practices in digital media and community networks. A meme is just a meme until you make a blockchain out of it. Thank you for listening and engaging. This is I also want to thank all the people in the Gina Lab, the research crew that we have, and thanks again for having me. This went a little faster than I expected it to, but we've got lots of time for conversation, questions. So,
perfect. Thanks. Okay, so I'll kick some off again. Just drop them in the chat, whatever your questions are. Do you see is there a potential, I guess, for memes to change behaviors or attitudes, or is that sort of just kind of kill the whole thing if you try and use it, say, educationally? Say there's some tricky concept like privacy and you want to get people thinking about it and you try and engineer memes, but would there be an uptake? Do you think it would actually change people's behavior, or people would just be like, oh, it's not funny, or I see through what you're trying to do here and just ignore it?
Mm-hmm. Well, I think memes in terms of media content is like it's the equivalent of the infographic, right? It's the biter-sized version of the infographic. So memes are seen as kind of playful and funny, but they're also seen as serious content as well, containing serious content. So they're ways of consuming complex ideas very, very quickly. Like that visual back about being about the pandemic, right? How I felt in 2019 versus how I felt in 2022. Well, it's a joke on the surface, right? What we call the denotative level, the surface level of consuming content and cultural content. What's underneath that is a very serious shared experience that all of us have of struggle, of shared fear and anxiety about what's happening in the world. So when that's a very serious type of conversation. So I think that's something like talking about all these different very serious topics is memes can be very, very good for that. At least entering into the conversation. Of course, when you're talking to students in a pedagogical context, you want to get into some of the deeper issues, but at least you're getting their attention.
Okay, I'm going to ask you one other thing. It's not about memes, so I'm kind of rolling the dice that you'll have something interesting to say. But it to me seems sort of similar because it has an underlying culture. So, you use the example of Dogecoin. Are you familiar with Bitcoin maximalists? So these are people who, believe that Bitcoin is supreme and nothing else.
One chain to rule us all. The Lord of the Rings of blockchain space. Yeah.
Exactly. So maybe you can talk a bit about your thoughts, any thoughts that you have about how that emerged. To me, it strikes me almost as kind of like a religion. Anything interesting that you might have to say about that type of subculture emerging in the blockchain space?
Yeah. I mean, like Dogecoin as a community, Bitcoin also as a community, and that community, negotiates the value of Bitcoin and amongst themselves, and it's a bit of a head scratcher, to be honest. The Satoshi Nakamoto white paper, whoever that was, it might be male, might be female, might be a group, it could be, another type of trans identity, it could be Japanese, it could be from the West. We don't really know, but that white paper, those 8 pages were extraordinary. They were half, technical specs, and it was half political manifesto. So, it wasn't just let's make this cool technology, but this cool technology was a bottom-up grassroots movement against, the 1%, the centralized banking industry and finance industry, right? So it called a certain type of person to it, mainly libertarian type of ideology. And libertarian, while it seems, open and accessible and, Elon Musk's version of free speech, it also tends to be a little bit dramatic in the way that they see things, if not sometimes racist and sexist, to be perfectly honest. The interesting thing about there's research done on the ideology of Bitcoin maximalists, for example, and that libertarian one has they found quite fascist tendencies. I'm just repeating what scholars have looked at this. But when people looked at the Dogecoin community, it's quite different. It's quite accepting. It's quite intercultural in terms of and so it's hard to think that the accepting nature of Dogecoin as bringing people in terms of a community, right? It has had a lasting impact on why Doge has stuck around. Now, why the maximalists, continue to think there's one chain, I'm not sure, because what's good for all chains is good for Bitcoin. And so it's a curiousness. Of course, now they're having their day with with the new protocols and new utilities that are coming out of Bitcoin, with the ordinals and the BRC20 protocols, things like that. So all the Bitcoin is more than just Bitcoin in terms of the chain is starting to. We'll see what happens. I think this competition between Ethereum and Bitcoin is going to continue for a while. It's unfortunate it's a competition because we're all in the same small boat.
Right. And if you dig into the history of Bitcoin too, there is like Gavin Andreessen in the early days would go on libertarian podcasts, and that sort of brought an influx, I guess, of people as well.
Exactly.
Okay, so a couple of questions in the chat. So Preston asks, I'll just read it. Do you have any thoughts on memes as vehicles for dis or misinformation? And how does memes as economic marketing relate to culture creation? Are they the same thing, or is marketing something different?
Yeah. So a lot of the what I said today is going to be ringing is going to resonate with the marketing folks that are either later today or tomorrow. I noticed them on the channel, and memes are tools for culture creation, right? They're not good or bad for culture. They're the vehicles of negotiating culture. And meaning making is not something that's static. We don't Bitcoin doesn't have a meaning today like it was 10 years ago. That meaning has changed over time. For example, from financial circles, Bitcoin was non-existent. It just didn't matter, right? In the first few years. And then it started to pop up on people's radars around 2016, 2017, especially in the financial circles. But they started to see it as maybe something to invest in, or maybe it was just a big Ponzi scheme, right? Fast forward to, and the volume around the Ponzi scheme thing was quite loud. Fast forward to 2020, 2021, all of a sudden the volume around the Ponzi scheme gets turned down, and all of a sudden it gets started to being talked about as maybe a safe haven, as a investment asset. Its ticker is on every single Bloomberg, Morningstar, you name it, it's there along with Apple and Tesla, et cetera, et cetera. That's not because Bitcoin changed at all. The chain has been in constant operation for 13 years. It's never gone down. It's never been hacked, right? But the meaning around it, which influences the way that people see it and want to interact with it, has changed over time. And that's the process of meaning making. And that's where culture and the understanding of it, that's why the value around it hasn't been driven by any change in the chain. It's been driven by the way that people talk about and agree that it's useful or not useful.
Cool. Okay, next question. Great talk. Thank you, Peter. Given the potential and industry interests in blockchain and digital ledger technology, DLT, why do you think the uptake level in blockchain teaching and curriculum integration in universities in Canada is what it is now? So you mentioned, for example, you're the only person at SFU that's been teaching blockchain.
Yeah, I'm sure there's others that do lectures or touch on it or those sorts of things, but I have 3 full courses on it now, right? And the engines of the courses, the theoretical and the research engines are different, the topics, but I usually with my courses, I layer over a technology. I've been studying big data before it was called big data, and then social media. So these kind of megatrend technologies are the things that I feature in my courses to connect the students to the world around them. But now I started to learn about Bitcoin in 2015, 16, and I bought Bitcoin to buy Ethereum, to buy this thing called the DAO in the first major ICO, and then the DAO hack, and then losing it, and then the forking the chain. It was a fascinating time. And in 2017, I started researching this stuff full time, and my entire lab I pivoted towards this because I think it's that important. It's the third wave of the internet, and we need to understand this thing. Interestingly, I tried to get interest from my colleagues at SFU. It wasn't really being picked up, but I've been part of things that have been picked up. Like SFU wanted to establish itself in the genome space back in the 2000s, and I was one of the researchers that became part of that, and I've done a lot of work in that space. I was also one of the architects of the big data hub we have. So the university having a strategic move into big data, but this thing about blockchain is just. People I don't know what it is. It's taken a while for it to be adopted. Adoption of Bitcoin is somewhere just over 10% globally. So it's a lot slower than the second wave of the internet, which was social media. That was a lot easier to use. It was more accessible. So I still think it's a bit of a head scratcher. Like I said, I've been here before, and in 5 to 10 years, there'll be lots of courses on it, I'm sure. It just takes time sometimes.
Okay, a two-part question. So the first, I won't read the whole thing. You can probably just read it yourself. But the question is about the relationship between memes and sort of like the original, I guess, Dawkins like conception of it, of memetics and the sort of relationship to genetics.
Yeah, memetics, memetics tends to be, different disciplines study culture. Is there a lot of noise behind me? Can you hear that?
No.
Oh, okay. It's just
Maybe a little. But it's not distracting at all. It's fine.
Okay, because I can put my headphones on. Memetics is a way of understanding how we mirror culture and learn culture. And I believe it comes from anthropology. Different disciplines study culture slightly differently. They use different words to talk about similar types of things. I don't think, while Dawkins was prescient in what he was doing, biology, the biological understandings of how culture work don't fit. Right? Culture is not biology, and biology is not culture, right? Culture is a very nonlinear thing to study because humans are agentic and they make decisions. So while you may find a mechanic within culture, right, of the way that something works, 9 times out of 10 it'll work. The humans will do the same thing in a pattern, but then one time they won't. Not because the engine driving it fails, but because they just decide not to. Right. So, memetics, ideology, discourse, rhetoric, these are all trying to capture similar ways that we negotiate culture and how culture drives our actions and our value making, that sort of thing. I hope that helps. If it doesn't, just type it in. Number 2 is, Gregory, great question. Thank you for that. Can we agree that blockchain didn't evolve by natural selection? Blockchain. Yeah, I don't think blockchain evolved by natural selection any more than Facebook created the metaverse. So metaverse has been around as a concept and as a discourse and as a media representation for a very, very long time. New technologies and innovations, they're adopted on purpose, and they're adopted in part through a process of users, of people picking them up and using them, the classic Everett Rogers adoption curve, which you see in business schools all the time, where adoption goes from 0 to 100% over a course of time. And there's kind of 5 different groups of users that characterize those different stages of adoption. That's actually not a business, doesn't come from business school. It comes from Everett Rogers, who's a communication scholar. It's a very, very deep book that people use today to talk about the internet, but it was actually written about seeds and farmers back in the 1950s. It's an amazing, amazing text.
Okay, great. I think we'll wrap it up there. And thanks so much, Peter. And we'll give you a virtual.
Thank you for having me. I really appreciate it. Yeah. Thank you.
Okay, great. All right. So next we have 3 student postdoc talks. And so the first is from Syed Mohammed Dinesh. Can you unmute yourself and share your screen?
Hi, Professor. Hi, everyone. I'm so sorry. My camera just stopped working right before presentation, so I cannot turn on my camera.
No worries. Does your slides work?
Yeah, okay, sure. I'm going to share the screen. So, okay, so can you see my screen?
Yeah, we can see it.
Yeah, okay. So,
do you go by Mohammed or Dinesh?
you can go by Danish.
Okay. So Dinesh is he's a postdoc. He's currently at ETS Montreal, and also is at Hydro Quebec.
So can I start?
Yeah, go ahead, please.
Yeah, okay. So as introduced by Professor Jeremy, I'm currently doing postdoc in ETS, and we are currently working with Hydro Quebec on a project of introducing blockchain in energy trading and smart grid. So the title of this presentation is Securing Electric Vehicle Charging Networks Using Blockchain Technology. So basically this is, I'm going to present a paper where we proposed a blockchain system to secure electric vehicle charging network. It's more like the energy trading between the electric vehicle and charging station, and we are doing it like peer-to-peer. So currently, the EV service selection problem is something like this. You have a third-party provider which takes the electric vehicles service requirements and it takes the charging station service parameters. Electric vehicle service requirements include the charging cost, like the location of the charging station, like how much time it takes to travel or how much time you have to wait, and actually the charging time. So basically, different charging providers or different charging stations have different charging capacity. Some are fast chargers, some are slow. So we have to take this into account. And as an electric vehicle, I have this requirements that I need to see the price, the time to travel to charging station. So currently what happens is we share these parameters to third-party providers, and the third-party providers, they actually schedule the electric vehicles based on their parameters to the charging station. But what is the first problem? The first problem is we have private data leakage. So if you are sharing your consumption behavior or your location to a third-party provider or even your identity, your private data is not secure. And previously you have seen that even the Facebook or even the Google, they actually sell your data, your private data. And it's not really good for electric vehicle, because if you know the charging consumption or the charging behavior of an electric vehicle, you can actually see when the charging vehicle owner is outside of his home. And then we have trust issues. I mean, if you are sharing the private information, it can go to the charging station. And what if you reserve a charging slot at charging station, but the charging station actually see its benefit and it sells the same charging slot to another vehicle who is paying more? So these are the problems. So we come to a conclusion that the third-party providers, they are not really a good or optimal solution in order to secure electric vehicles' private information. So now we come to the problem statement. We have different charging service providers or charging stations. They have different cost, they have different locations. So as an electric vehicle with my current location, I can actually calculate the time to travel to these charging stations. So considering these different requirements and the dynamic pricing offered by the charging station, we need to consider them in our problem. And then we have different service requirements of electric vehicle owners, like some prefer price, some prefer short distance, some prefer fast charging time. So based on your preference, we need to make a reservation at the charging station for the charging slot. So instead of sharing all the information to a third-party provider or the charging station itself, we can actually get all the information at the EV's premises, and then we can solve a problem of maybe selecting the best charging station out there to charge your electric vehicle. And since we are not using any third-party service provider, we can utilize smart contracts to reserve the charging slot at the charging station, and we can perform payments through crypto or through the smart contracts. And again, without sharing any information to third-party provider, we can actually store this information on smart contract, and then we can actually improve the privacy of EV owner. So basically the contribution of this work is we proposed a theoretical model for the optimization problem of decentralized CS selection. So we have actually modeled it as an optimization problem, and the electric vehicle is solving it to get the best charging station out there among all the available charging stations. And we propose a decentralized efficient CS selection mechanism by individual electric vehicles without sharing the private information. So I'm going to explain how we are solving this optimization problem without sharing the private information out there to the charging stations. And finally, we are not using any third-party providers, so we are proposing a private reservation and payment mechanism with guaranteed availability at the charging station, while enforcing interacting entities to honestly honor the reservation and payment mechanism in an untrusted environment. So everything, the payment and the reservation and the authentication, it is being done on the smart contract. So these are our contributions. So now I will give you a little bit idea about the related work. So actually this work got published in 2021, at the end of 2021. So I'm going to explain the related work before that. So basically scheduling has been a main problem in electric vehicle charging station or even in the energy trading. So the scheduling decision is normally taken by the central aggregator. You give your requirement, and the central aggregator actually schedules you maybe a charging slot or maybe some energy if you want to buy. And what is the problem? It leaks personal information with the central aggregator and charging station, and you need to trust the aggregator with your private information. Recently, like before the paper, there were some auction-based frameworks actually leveraged blockchain network to actually secure the private information. But what they were doing is they were storing the private information in the blockchain network. So it was still exposed to the charging station, and then they were doing all the transactions on the blockchain, which could lead to high blockchain's transaction and storage overhead. And in those works, like the problem was not formulated theoretically, and they were just saying, okay, we can select or we can match the charging station with electric vehicle, but how? It was an open question. So in our proposed architecture, it's more like a peer-to-peer energy market for electric vehicles, where we have no third-party service providers. So we have this electric vehicle like Alice, and it is in the vicinity of roadside unit RSU, and these RSUs are connected to the charging stations. So what happens is the charging stations actually broadcast their charging information to the roadside units, which are deployed by the government, and they relay this information to the electric vehicles. And after getting all this information, the electric vehicles can select the charging station locally without sharing any private information to any entity in the network. And using an offline channel, they send the reservation request to the blockchain network to the charging station. And here the third party is replaced by a smart contract to enforce reservation, authentication, and payment. So we are storing this information in the smart contract, not the personal information, but the reservation information that, okay, this vehicle has this charging slot at this charging station at this time. So we actually formulated the problem as an integer programming decision optimization problem, where we had like one decision variable, and this decision variable actually depicted the selected charging station. And we created an objective function which was composed of 4 different costs: charging monetary cost, traveling time, charging time, and waiting time. We can add more variables too, but in our paper we considered these 4 important variables which needs to be considered while selecting a charging station. And finally, we calculated, so this is our optimization problem. If you want to get more information about it, you can refer to our paper. So we solved this optimization problem off chain because it's not feasible to solve it directly on the blockchain, because it can take high gas cost. And again, if you want to solve it on chain, you have to put the private information in the smart contract, which again leads to the privacy leakage. So calculating this problem off chain actually led to solve the privacy leakage issue, and it eliminated the performance bottleneck of blockchain. So basically, this is the blockchain-based EV charging protocol which we proposed. So we have this charging station which broadcasts the information to RSUs, and this information is given to the electric vehicles. Now it can be done either through publisher subscriber model, or maybe EVs can subscribe to, or it can, this information can also be sent using 5G or 4G, like it depends what model you want to consider. And after solving the optimization problem, the EV selects the charging station, and then it reserves the charging slot at the charging station on the smart contract. And once the charging electric vehicle, it goes to the charging station to charge itself. The charging station is going to authenticate if it's the right EV. And then electric vehicle is going to pay to the charging station through the smart contract in the form of tokens or crypto, or like any predefined method. And then this protocol ends. So basically we are getting 4 things here. We don't have any trusted intermediary, and then we are performing efficient charging station selection. Since we are sending all this the charging information to the electric vehicle is not sending any information to the charging station or any entity, and that's how it is remain private or pseudonymous. I'm using the word pseudonymous because at the end of this presentation, I'm going to tell the problem with this current framework. And the reservations are guaranteed. So once the reservation is made, there is no like conflict of the reservation, because it is being done in the smart contract and it cannot be changed. So for the implementation, we actually took the reference implementation. We get the data from US Department of Energy website, and in New York, there are a lot of charging providers who have deployed their charging station in the New York, just New York. So we took the data of New York, and you can see in the graph that there are different pricing of charging stations, and then there are different charging powers of these charging stations, which are deployed overall in the New York. And we implemented the smart contract in Solidity, and we solved the optimization problem through Cplex. And then we deployed, we used the public Ethereum network to test our blockchain functionality. And for the performance of Block EV, we check the performance in terms of computation time and pricing comparison. So in the first graph, in the computation time, as the number of charging station increases, the time to solve the optimization problem to select the best charging station also increases. But again, it's not, the search space is not really big. I mean, maybe there are 100 or 150 charging stations. They are not a lot. And if we consider the range scenario, let's say a charging station is only looking for the charging station within like 5 kilometers or 10 kilometers, then the search space becomes small. And for the pricing comparison, we actually selected the charging station randomly among a set of charging station, and then we tried to select the charging station with our optimization problem. So we saw that our proposed system actually selects the charging station with the least price. And also for the performance of the blockchain, we saw it in terms of transaction and storage overhead. Since the graph is linear, because there are like 3 or 4 transactions which need to be done with the charging station from electric vehicle to reserve the charging slot. And as the number of electric vehicle increases, or as the number of as the number of electric vehicle increases, the number of transaction and the communication overhead in kilowatts, it increases linearly. And we compared our work with the baseline, which was an auction-based mechanism. And our work is actually the extension of this research paper, which was privacy preserving blockchain-based electric vehicle. In this paper, they proposed an auction mechanism, and they were storing all the private information on the blockchain network to perform auction. So this is actually, in the presentation, I use the word pseudo-anonymous. Why? Because right now, all the trading mechanisms which are being proposed in the literature, actually they are missing a big point here. So when we are making transaction with the smart contract, actually you are doing with the blockchain address. So when there is a sender and when there is a receiver. So when you have made a reservation and you go to the charging station premises and actually you pay for the charging services, now anyone can see, okay, this is the electric vehicle with this plate number, or maybe this is the owner. He has the blockchain address. So once they search the blockchain address, let's say on Etherscan or any blockchain with the history, they can actually see all the charging history of that specific person. So now this is this is not truly anonymous. So this is pseudo anonymous. So once we can see the blockchain address of an electric vehicle, then we can actually see all the charging history of that person, because the reservation information, it's not encrypted and we have stored it directly on the blockchain. Let's say this address has this charging slot. So maybe people can see, okay, this guy actually takes this electric vehicle to this charging station every day at 5 p.m. So we can actually see the charging behavior. Again, this is a privacy threat. So we have actually extended this work, and it is currently under revision, where we used like ring signatures to solve this problem. So basically, in all the papers where the trading is being happened, it can be energy trading or it can be anything. This problem always persists, because when you know that this guy has this blockchain address, we can actually see the history. There are a lot of solutions we can use. We can use ring signature, we can use stealth address. Even we can use zero knowledge proof, or Monero blockchain is a really good solution for this, because it hides the sender and receiver address using ring signatures. But again, if you are transacting on the smart contract with some data, then you have to keep in mind that you are not just transacting the money. And since Monero blockchain doesn't support some smart contracts, so you have to come with a solution how you can secure the electric vehicle's identity on the smart contract without exposing the blockchain address at the charging station premises. So yeah, that was all about the presentation. Thank you for listening, and any question?
Great, thanks. Yeah, so again, if you have any questions, just drop them in the chat. So I'm reading between the lines, but you're envisioning this on like a public blockchain like Ethereum. Otherwise, you would need all those privacy guarantees. Have you thought about just using a private blockchain like say Hyperledger or something instead of Ethereum? Would that solve your problems or?
Yeah. Exactly. So basically, the motivation of our work was, since the charging station and the electric vehicles, they are private entities. Yeah, you can involve government and you can make some consortium or private blockchain. But again, in the private blockchain, there are some entities who are going to manage it. But who are they? They can be government. Yeah, we can solve this problem. But if you are just considering like a peer-to-peer energy trade, then our motivation was to, since all these entities, the transacting entities are private, so public, so we should use public blockchain for that.
Perfect. Okay,
Yeah.
I'll read the question in the chat. You can also look at it and read it yourself. Thanks for your nice presentation. If CS gets compromised and acts maliciously, for example, does not do the reservation, or it does not meet the expectations of EV, is there any mechanism to help the EV prove it and get refunded? So is there sort of accountability or dispute resolution?
Yeah, exactly. So actually we have, this is an open problem. Again, we tried to solve it in our current paper where we use trusted execution environment, where maybe it can run in the smart contract, in the smart meter, and electric vehicle can directly send if it is charged or if it is not charged, or the exact state of charge, to the smart contract, and smart contract can perform the conflict resolution. But yes, it is an open problem. And we are trying to work on it, and we are actually looking in the direction of trusted execution environment to solve this problem.
Okay, great. So thank you again for the talk, and we'll give you a virtual round of applause. So these student talks they'll go a little bit quickly. Next we have two students from the University of Manitoba, if I'm not mistaken. Yes, and so Kusha and Kirarash, hopefully I said that decently. You should have permission to turn your video on. Yeah, okay, so I understand you'll sort of present half and then switch it over halfway through.
Yeah, hi Jeremy, hi everyone. Yeah, actually you pronounce our names correctly. I'm happy. And yeah, first I will
didn't
start
do
the
the whole
presentation.
last name and stuff too, so that's
Yeah, that was too long actually. The point is I will start the presentation and then we will switch, and the Kirash will continue my job. So let me just share my screen. Okay. Okay. I guess now you should see my.
Yeah, we see it. It's not full screen yet, but we do see it.
Yeah, that's great. Okay, can I start?
Yeah, go. It looks great. Here you.
Okay, great. Thank you. So, hi everyone again. Today, actually, my name is Kusha, as you heard, and today my colleague Kirash and I will introduce our new blockchain-based loaning system named Calysis. I should just mention a point that this research is the result of a collaboration between Future Data Lab and TCDT Lab of the University of Manitoba, and it was accepted as a demo paper in ICBC 2023. So let's start. Okay, in this presentation, we will talk about our motivation, our contributions, our methodology, and evaluation. Well, regarding our motivations, well, like any other research, we are here trying to address some challenges. The challenges that we are going to address is all about the budgeting for small businesses, especially in the realm of advertisement. Usually, as small businesses have to spend near half of their budget on the marketing. And well, sometimes it could be really expensive, but it's not really affordable for small businesses, especially the ones who actually are newcomers in the whole business area. And also, there is no guarantee for success. You can spend all of your money on a billboard or something, and maybe there will be no even one single customer. The other problem here is struggling with attracting Gen Zs, because these traditional ways of advertisement, they just don't work anymore to attract younger people and Gen Zs. And being a minority can really worsen the whole situation for the small business owners because of just discriminations, that all things that we are all familiar with that. So people involved here are small businesses, especially the minorities, startups, entrepreneurs, and normal customers, and also the Gen Zs. So let's look deeper in the challenge. Well, in the Canada, actually, we have about 1.2 million small businesses. In our city of Winnipeg, there are about 20,000 small businesses. All of them have some struggles with advertisement and drawing the attention of their customers. And unfortunately, about half of them cannot survive after 10 years. So these challenges make us to think about what can we provide them using a blockchain to overcome their problems here. So how can we do that? Well, we will try to giving them a platform for marketing and, especially for getting a loan and spending on the marketing in a very purposeful way. But there are three main actors here. The first one are business owners. They usually have some barriers. For example, the main one is just budgeting problem. And also they have some struggles with attracting new customers from younger generations. And sometimes they do not know how can they, they lack of information about how can they spend their money wisely and, to just gain the maximum benefit that they can. So here we will give them a platform which can actually cover the budgeting problem. And also our platform have a gamification part that can attract new younger generations and even normal customers. I mean, the customers from the, not very younger generations, the middle age and this thing. And also our platform can doing the funding allocation in a very wise manner, which can help them to just avoid wasting the money. And about the customers, which are our second actors, well, our platform will give them money and fun simultaneously, because we have a gamification which is based on augmented reality, and through just playing a game, they can earn some coins and assets, which they can use then to just earn some money or buy stuff from the business owners. And also we believe we can draw their attention, because just it's not like just some Instagram campaign which is based on some edited videos. In our platform, actually, and using our gamification, the customers can actually go inside the store and verify the validity of the store. They can check if we are telling truth about the store or not. The last actor is financial institutes. Actually, we can give them, using our platform, they can actually increase their income. They can earn more interest rates, because they can, everybody can use this system to just get a loan. And also to getting a loan, they have to be a customer of the bank. So there are gonna be a lot of more accounts opened in the bank. The other benefit is actually they will be the financial institutes will be adapted to the newer technologies like blockchain, augmented reality, which we all know that, being adapted to newer technologies, a company can survive more than the others, or they can beat their, rivals. So how our system can cover those items? Let's look at our system. First of all, let's look at it with a higher abstraction level. In brief, our system is a blockchain platform which can lend money. And it has another component, which is a gaming component. It can attract customers, and it can, it contains some quests and challenges. These quests and challenges are designed by the shop owners using a very simple UI. So they're gonna be literally some quests in a store, and people can go there and solve the quest. And after that, there are gonna be some rewards for them. So they're gonna be money distributed among the winners, and through that we can have some monetary incentive for the people. And as it's a game, they're gonna be an emotional incentive for the people. So, and the last point is money will spend where it must be. We mean the money will be spent only when there is literally a customer in the store. So it's not like just spending on the billboard. We don't know what is the result. There's a customer in the store, and then you spend your money. So let's again make our look deeper and see our components here. Well, our system has these 5 main components. The first one is the user components, which is an augmented reality engine. It has also user APIs and user interfaces that customers and entrepreneurs can work with that. Customers component are, just our ordinary customers, Gen Zs and gamers, as I said before. And about our entrepreneurs, well, they're gonna be business owners, especially minority business owners, which can use our user components to just, gain some benefits. The other customer is our on-chain component. Well, we used Hyperledger, and we have some smart contracts on that and token issuance. And our last component here is a core banking component, which we will just give banks some APIs so they can generate some tokens, and they can use that for token exchange with the fiat money. And also they're gonna be a loan management system. And it's actually literally a component which is totally related to the bank. Okay, so here is our infrastructure. For using our infrastructure, usually banks and financial institutes should create a consortium, and they can map their consortium to a Hyperledger channel. They can apply their policies to the channels using channel configuration and network configuration. And also, these banks and financial institutes should provide systems with some nodes, like peers or ordering nodes. And also, there are gonna be some applications for that. These applications will serve actually our customers here, like Gen Zs. They will serve the business owners. They can use these applications just to distribute the rewards among their customers, which are actually in their stores. And also they can use the application to repay their loan. And also they're gonna be a third type of applications actually, which banks or financial institutes will usually use. They will use this application to just distribute their loans to their customers, and also to just manage the whole loaning repay system. So here was the infrastructure of our proposed system. And let's look at the way more intuitive and a detailed scenario of our system, which will be discussed with by my colleague Kiara here. So I guess now Kiara should share the screen. Okay.
So hello everyone, I hope you could see my screen. So thank you for having me, and I'm also from at the University of Manitoba Future Data Lab, and I will present the rest of our presentation here today. So basically, first of all, I want to have a kind of intuitive example, step by step, to see what's going on, especially exactly on our system. So the thing is that, as Kusha said, we have like three different roles here in our system. So we have from one side entrepreneurs and bank and all kind of financial institutes for lending money from other side, and also we have customers that are looking for a kind of things or goods here. So the way that we want to start this is like the entrepreneurs have like their own businesses, and they request and they need some kind of money for extending and attracting some users. So we have like the concept of customer attraction loans right now in all of this traditional loaning system. And the thing is that all of these traditional systems start with a request from entrepreneurs. So first of all, in our system, entrepreneurs should request for a kind of loan. And this loan is a customer attraction loan here in our system, so the title is. And after requesting for a loan to a bank, so the bank will validate and see like some documents and validating the entrepreneur, and then will issue some tokens basically from the token issuance infrastructure blockchain base. And issue this token and send like this token directly to the entrepreneur smart contract. So basically in this system, we have like a kind of a smart contract for all of entrepreneurs specifically. So all kind of entrepreneurs, they have their own wallet and they have their own entrepreneurs. The thing is that after issuing like this token, these tokens will go like to this wallet, and entrepreneurs cannot like spend this money directly. So they need to use this money based on a kind of a smart contract that I will explain in detail in the future. So in step 2, we get the tokens in the wallet of entrepreneurs based on smart contracts. And next, in step 3, so entrepreneurs have like these tokens in their wallet, but they cannot spend it. And basically for using this loan, they need to somehow using a kind of quest, and we provide a kind of very simple UI for them. They can like create some very easy AR quest. It's a kind of Pokemon Go AR games, but it can be somehow educative on all kind of quests that they want. So it's basically some steps, and they created some steps, and these quests should be a kind of physical activity in the business location. So it can be finding some goods, it can be have a kind of game scenario, finding something, it can be like all kind of different AR platforms. We can support these things in our platform. So basically they design a kind of quest, they assign the prize amount. So basically, like as you can see in this picture, this is a prototype of our system, and if you can see, so we have like 2 tokens for ending like this game, for example. So after designing some quests by entrepreneurs, we switch to step 4 and 5 together. So we have like a list of some games here in our application. So customers will go to this application and look for a game that's near their location, or maybe they are interested into, based on also the price of that. They will choose this, game quest. They will play that and finish that. And after finishing this, so we have like a double-signed smart contract here. So they finish this quest. They like send the request to smart contract as a finished quest, and from the other side, entrepreneurs should also sign the smart contract at the other side, and then the prize coin will go from the wallet of the entrepreneurs to the wallet of the customer. So here for the customers, we have like both sides of incentive. So we have like the emotional one. It's a kind of playing game. It's a very, it's a kind of entertainment thing. And also we have the monetary part of that. So the customers, they are actually gaining some money here. And this money is a kind of monetary token. It's part of the loan that entrepreneurs take from like the bank here. And if you see this part of the system, if you look at that, so you can realize that entrepreneurs cannot like assign any kind of money or directly spend this money on any kind of purpose, because the system will assign the users to this location, and after that, entrepreneurs will give them the money. So the money is a kind of purposeful money, and the spending of that is really, related, and it really depends on the users that are in the location of that business. So after that, we have like these customers, they earn some money, and they have like two options after that. They can like redeem this token to bank and get the fiat money. So they have like actual Canadian dollars, for example. And or they can also purchase some goods and some other things from the entrepreneurs, or get some services based on this token. So in this way, we can like make them to circulate this money in our system, and in this way we have like more token circulation in the system. And this is a part of any blockchain based token. So we want to increase this. So we can also incentivize user to use these tokens as a purchase method. So we have like put more discount on that. Or also the thing is that entrepreneurs should only repay the part of the tokens that they purchase for the customers. So basically in this step, customers have two different options. As I said, the redeem or purchase again things with this money from entrepreneurs. And at the last step, so we have the loan repay mechanism. So the entrepreneurs should repay just the part of the loan that they spent. So basically, this is the part of the loan that customers redeem. So because if we just pay this token back to the wallet, so this is again in the wallet, so they don't need to repay this part. So this can be another incentive for an entrepreneur to like motivate customers to use this token as well. So after that, we have like lower interest rate for entrepreneurs if they want to repay with tokens, and also higher interest rate for them if they want to repay the fiat. And again, they just repay the part of the loans or tokens that they spend. And they have like the actual customers in their business. So it's not a kind of prepaid marketing and advertising way, just like the traditional one. And also it has like lots of revenue models for and industrial incentives for the bank and financial institutes. We have like loan interests, we have transaction fees, a very flexible one. We have more customers and deposit, and also we have the token issuance power. So we have lots of advantages for the banks because they have like their own token issuer network. And this was a kind of abstract scenario intuitive example for our system. And in terms of evaluation, so the thing is that this work is under development. In this section, we want to do like some evaluation to show that our system is working perfectly, and it's better like than the traditional system. So we want to evaluate our system for all different actor sides. So we want to evaluate it over customers, to see that customers like the system more than the traditional one. We want to evaluate it for the banks, because this is a kind of a three-side model. We have different three-side actors. In one end, we want to evaluate it for also the banks and the entrepreneurs. In terms of the banks, so they have like some security and transparency advantages here. So they have like, and this is thanks to blockchain infrastructure. So we have like a smart contracts, everything is automated here. We don't need any intermediate company or third party. So there is a kind of very cost efficiency here, and also the transactions are immutable, and we have like more transparency and privacy here for the bank system. And and we have like some economic consideration as well. So in this part, we have three different subcategories. We have interest rate calculation in our system, because this is basically all this infrastructure is a kind of native infrastructure. We can have some accurate and fair methods for calculating these interest rates. We can also customize these interest rates based on the users, because we have like the background of this entrepreneur. We know how is it going on in his business, in his or her business. So the thing is that we can, hire or apply lots of different innovative methods like federated learning or all of this kind of machine learning to learn more about the entrepreneurs and have like more accurate and customized interest rate here. So because everything is in our native built-in infrastructure. The second is our cost efficiency. So we want to evaluate our system over transaction fees and costs associated with that compared with traditional lending mechanisms. So we know that here in this system, We don't have any third party or intermediate company to do like loan allocation or even advertisement things. So we reduce the fees and costs associated to the marketing process significantly. And also in terms of business efficiency, we can make sure that all the entrepreneurs will spend this money to, attract users. And this is a kind of exact thing. So they have like the customers and then they spend money. So this is a kind of business efficiency. They don't waste money here for advertisement and marketing. And as Kusha said in the first part of our presentation, the main reason of failing lots of this company is lack of fund, and they spend like more than 50% of fund in the marketing. So if we can like address this problem in this business efficiency fund, we can like increase the chance of these small businesses more than 50% to survive after like 5 years. And the last thing is evaluation and over like the customers. This is a kind of HCI and fairness factor. So we have like two different criteria here, and actually three: fairness, usability, and system perception. We want to know that if the customers also think the system is fair and it's usable. And that's all. So this is still, as I mentioned, so this is also a kind of ongoing research. We are working on evaluating this research in all different domains and all different users. And thank you for having us here. And if you have any questions, you're more than welcome to ask. Thank you.
Great, thanks. I'll just kick off. We maybe have time for one quick question, but so you mentioned you use Hyperledger, so you're in the permission blockchain model. I was curious, who do you envision playing the role of the validators, like the nodes on Hyperledger? Like the bank obviously would be involved, but like who else to make it somewhat decentralized? And then what's their sort of incentive? So I was expecting that maybe they would get some fees or something like that, but it wasn't really clear.
Okay, yeah. First of all, about the validators and peers, all the peers will be provided by the banks and financial institutes, because well, they are the owners of the whole process and money. They are serving the customers and entrepreneurs, but the owners are financial institutes. So validators and hold the policies will be determined by the banks. And about the other part, well, we have two options for that, and it really depends on the business policy of the banks. So the main policy for banks' income is actually the interest rate from the loan, but depends on their policy. The transaction fees might be available too. But as I said, it really depends on the policy of the banks.
Got it. Okay, great. Well, thank you both for presenting, and a virtual hand clap for both of you. And
thank you.
Okay, so we'll move on to the last talk of the day. So Shashank, are you able to share your screen?
Yeah, can you see my screen?
Okay. I can see your screen and hear you. So as your slide says, you're a PhD student, I believe, right, at U of T.
Yeah.
Okay, take it away.
I'm sorry, just give me a second.
No worries. We see it, but it's not full screen.
All right. I'm sorry.
No worries. Take a minute. Everyone can get up and stretch if you have to. Can I help you troubleshoot it? Is there a specific issue? I can always show the slides on my computer and you can just tell me to advance if. You're muted, you're muted.
Okay. I could just share the slides. I don't see where the screen is going. All right, this should probably work. Can you see it right now?
Yeah, perfect, perfect.
All right. Hi, everyone. So I'm Shashank. I'm a PhD student at University of Toronto, and I'm here to present my work on analyzing geospatial distribution in blockchains. This work is done with my advisor, Arno Jacobson at Middleware Systems Research Group. So before we dive in, let's ask, why do we need blockchains in the first place? What is the key point about it? So if we look at, like I asked the same question to ChatGPT, and what is interesting is the first point here, which is decentralization. Decentralization just means that we don't have a trusted authority or a trusted third party, which is at the center of transaction processing. So with that in mind, like if there's no, like if decentralization is not a big issue, then we have already solved all the problems which we're trying to solve with the blockchains in centralized computing. So the next question to ask ourselves is, have we reached the pinnacle of decentralization? Is this something we could do better? So decentralization is a complex concept involving social, political, and economic aspects, which are being based on top of technology. So it is really tough to understand all the multiple dimensions while taking into perspective on how far we have reached. In this work, we are looking at one often overlooked but a quantifiable dimension of decentralization called the geospatial distribution in the consensus protocols, which are responsible for transaction processing. So this is the distribution of validators in Ethereum. Right now, as you can see, like the validators participate in the consensus protocol and hence contribute to the decentralization of the blockchain. So you could see that 70% of the validators are concentrated in two regions, like namely US and Germany. This is not the problem only in Ethereum. We also have got access to another blockchain called OL.network, and we found that most of the validators here are located in two regions, US and Finland. Like then we asked the question, like based on the other metrics which we have been collecting on this blockchain, is there a limiting factor for validators joining from other areas? Say, we have seen some validators join from Singapore and Australia, but they haven't sustained in the network for a long time and they had to drop immediately for not meeting the performance requirements. This is fine, but like this, an important question to ask before we go into this problem, like, do we really need the geospatial distribution? That being said, like there are few of the concerns which we came across recently. The first one is robustness of the network. Say if all the validators are in one data center and like that region is affected for whatever reason, could be due to a war or a natural calamity, which could be out of humanly like control. And it is a central point of failure. Also, there are a lot of decentralized finance applications being built on top of blockchains, and being close to a validator might let your transaction go through quickly due to lower latencies and could also add to a little bit of more fairness, and also regulatory action. If you look at the current validators, like what if all the validators are located in a region, say North Korea, and we have to abide by regulations of jurisdictions which we might not even know just because the underlying network is running over there. So the challenge which we wanted to address here is the geospatial centralization in the blockchain networks. So to get started, first we want to analyze this geospatial distribution of the validators at the consensus layer. Then we look into the factors which are inhibiting the geospatial distribution, and finally address the factors which are restraining the geospatial diversity. So one of the key hypotheses which we had while starting the study was that the geospatially distant validators, which are often referred to as the minority validators in the study, are marked as crash failures, that they are losing their availability just because they have higher latencies, and they are considered as crash failure by other validators, is our hypothesis going into the study. So to approach this, we first built a tool called Geodeck, which is an emulator for the consensus protocols, which takes in arbitrary locations and shows how the performance varies. Then we prove that geospatially distant validators are being disadvantaged. They're being punished for not performing as per the threshold requirements. And finally, we are looking to address this problem. So before we delve in, let's look into some of the background. Like consensus protocols, even for blockchains, could be classified based on how they reach finality into two categories. We are looking at classical BFT consensus protocols, which have deterministic finality, and generally a set of validators, and these validators are fixed for a particular epoch. Epoch is a fixed duration in time with a constant validator set. And one in each round for a new block to be proposed, there is a block proposer. This block proposer could be chosen either randomly or round robin way, or based on the amount of stake they have in proof of stake blockchains, or could be other methodology. And once this block proposer proposes a block, we are trying to reach a quorum. A quorum is 2/3 of majority on that particular block. And once we reach a quorum, that block is appended onto the blockchain, and the validators get their reward for contributing to the consensus protocol. Now, the rewards is actually interesting because it makes us question who should be given the rewards. And what we have seen is most of the blockchains use some performance metrics to measure how well the validators are performing in that particular epoch for that consensus rounds. So liveliness is a measure which could be used for the performance, which is nothing but the number of blocks a validator has signed to the total number of blocks committed in that epoch. So this helps in measuring the performance and also giving rewards only to the validators who are genuinely contributing to the network. In our past work, we've used game theory to show that to counter the free riding and nothing at stake problems, the validators only with the liveliness, with above a particular threshold, have to get their rewards. Everyone below the threshold have to be penalized in some form. It could be either in terms of slashing, that their native tokens are being taken away from the from them by the protocol, or it could be through jailing, not letting them participate in the next consecutive epochs as a validator till they are back available and active. So with those information in the background, let's look at the emulations of the real world networks which we have done on the tool. So we used hot stuff consensus protocol, which is used in DM blockchain and a lot of other DM variants, which is also similar to Tendermint. And we have emulated it on the Compute Canada cluster. Now, Compute Canada cluster is a local area network. So to mimic the wide area network configurations, we have taken the pairwise latencies between different cities. This is provided by the Wonder proxy, and then we use NetEM, the network emulator tool, to emulate the properties of a wide area network. So say someone inputs different cities, say C1, C2, and so on up to CM, and the number of validators running in each city, IJ, and so on till P. Now we take the pairwise latencies between C1 and C2 and try to filter the IP addresses and say that this is a latency set between these two particular IPs. And the output of this is the liveliness against the city. So we are trying to measure how different cities are performing in a particular scenario for the hot stuff consensus protocol. So we have replicated the behavior which we have seen at OL. So OL.network, where most of the nodes are in Finland and US. We've just taken two cities for easy demonstration. And then we have also added some cities, say Melbourne and Singapore. And then we have seen that these two locations have almost zero liveliness as compared to the other locations. And in this control setting, it's also true that these nodes are active and they have synced their ledger to the latest state, but it's just because of the small latencies issues which these nodes are not able to keep up. Also, we've introduced this metric called Geospatial Diversity Index. This is a metric used to measure how distant a validator is from the rest of the validators. For this, we only consider the quorum, the closest 2/3 of validators. The reason being a quorum, like if a block is proposed, a quorum is formed with the 2/3 of validators. We don't necessarily care about the rest of 1/3 validators in the quorum. And we've used Haversine distance between the validators. This is because of we want to consider the spherical nature of the Earth, and latitudes and longitudes were used to measure the distances. And the GDI in an epoch for a validator is defined as the summation of distances to the closest 2/3 validators from itself. And as you can see, the GDI value depends on all the validators, not just themselves. And each epoch, if there's a change in the validator set, if there's a reconfiguration, then the GDI value also changes. Similarly, we define the GDI for the entire blockchain network, which is the average of GDI of each validator in that particular epoch validator set. So now let's get back to our problems and use this emulation tools to see if these are real things. Let's say that, let's look at the intuition behind why minority validators are having the low liveliness. Now, there are two cases for each block proposer. The first case is minority is not a block proposer. In this case, a node which is not minority is proposing a new block. And as you could see, the minority is further away. So all the blocks which are closest to it respond quicker, and a quorum is formed among themselves, assuming all the validators are active and running. So the minority is not gaining any liveliness over here. The second case is, what if the minority is a block proposer? Now, firstly, the case of this, the probability of this case happening is really low if we just use round robin or randomness. It also depends on how the block proposer is being selected. And even if the minority block proposer is selected, there could also be the case that in a partially synchronous model, the block being proposed might not be heard by the other validators in time. Within the delta time, which was set, the probability of a minority being a block proposer and proposing a block successfully might be a lower probability. So as you can see that minority validators have a low liveliness. Let us now use the simulator tool, the emulator tool, which we just built, the geodeck tool. So we are running some experiments with 16 validators. We have set different locations for minority and majority, and we have just been increasing the number of minority validators from 0 to almost half. As you could see that the liveliness when there's only one minority validator is pretty low. It's less than 2. And then as the number of minority validators increases, the liveliness is also increasing. As you can see in this graph, there is at almost 7 minority validators, we could see that there's an overlap between the minority and the other validators. This is just because they are able to form their quorums and participate in the consensus protocols more. We've also seen there's a strong correlation between the liveliness and the GDI, which was taken for the quorum for a validator, which just shows that this is playing an important role in how they are performing in the set. So now, that being said, we have 2 issues to look into. One being, how do we save this minority validators? The other being, how can we increase the diversity of the validator set itself? So let's look into the first issue, which is more pressing at this point, to save this minority validators. So we wanted a solution which is easy to integrate onto the current blockchain protocols, which does not open new attack vectors or trust in another third party. And it has to take the underlying security assumptions of the blockchain protocol itself. So what we came up with is a GDI exception smart contract. So a minority validators nominate themselves to just say that they are one of the minority validators. And then all the validators do a check if they are minority or not using a light version of this geodeck, which is just giving them the GDI indices. The validators then vouch for a minority validator. Once we have 2/3 of vouchers, this is added to the ledger as a minority. When a reconfiguration is happening at the end of the epoch boundaries to select the new validator set, the consensus protocol calls this function and looks into the set of minority validators. And if a quorum is met, and these validators are given exemption from being punished, either jailed or being slashed for not participating actively. We've seen that we've run some more experiments on a 16 node validator set size. We have seen a quorum forming between US and Europe. That was one of the constraints we have kept. And we have chosen randomly the other validators from the rest of the 242 cities. Now, here the thresholds pi have been increasing from 5, 10, 20, and 30. You could see that the more higher the threshold is, the more number of validators are being jailed. And all this could have been prevented if and only if there was an option to just mark them as minority and just get an exemption for themselves. We have also extended the experiments into 64 node cluster. And as you could see that as the number of minority jailed are increasing with the threshold. And also the other interesting thing is that what we have designed the consensus protocols to be is to increase decentralization. But if these validators are being jailed, there's a decrease in the total diversity of the geospatial diversity of the blockchain, and in fact, reducing decentralization by design, which could have been easily stopped using a smart contract, which could protect these minority validators. So to conclude, we designed and developed this geodeck emulator, which could mimic a real-world blockchain network, and as if it's running in different locations for its validators. And then we prove that the minority validators are being punished for providing diversity to the blockchain protocols. And then we present the GDI smart contract to preserve the higher geospatial distribution. Yeah, thank you. And if you have any questions, please go ahead.
Thank you. Thank you. That was awesome. I have at least 3 questions for you.
Sure.
But if other people do, they can chip in. So the first thing that comes to mind is, what about sharding? Could you do like a geographical sharding where, different islands or pockets of people work on shards, and then occasionally, of course, you have to bring them all together, but then that can be kind of like a slower consensus model.
Yeah, that's really interesting because I've been thinking about it, but I didn't really I mean, it's feasible. But right now, I'm just focused on the current permissionless blockchains and looking at how they could improve their geospatial distribution. I think sharding also helps in a way that based on geolocation, because most of the transactions might just be happening locally, and those could be easily handled if such a system exists.
Right. Yeah. So it's proximity to the transaction, but also just like taking quorums amongst people that are close to each other, and then having a big global quorum.
Okay, I see what you're saying. Like a signature aggregation locally and then integrating them. Yeah.
Right. Exactly.
That's a good idea.
Okay, and I know you're obviously focused on like the BFT based world, but what can you say about proof of work based protocols? Is it a worse problem, do you think, or not so much of a problem?
I mean, even there in proof of work, there is centralization like geospatially, but like this solution might not really apply over there, but they are like, there's a problem of geospatial centralization in general.
Right. Okay. And then the last question, which you might have covered, you might have had it buried under one of the variables. I just didn't catch it. But what about just the block interval time? So like, it seems the shorter, like if you're trying to do updates every 2-3 seconds, that's going to be a big problem. If you're like Bitcoin, you're just updating blocks every 10 minutes. It seems like maybe it won't be such a big problem.
Yeah, so when I'm talking about this BFT protocols, they are assuming the block interval time to be really small. Like they might be blocked, like the network OL, which I've looked into, where the blocks are being produced like 2 blocks per second or something around that speed. So it does work in those cases.
Okay. So that's super fast actually, to try and do more than 1 block per second, but yeah. Okay, I don't see any questions in the chat. So thank you very much. And
thank you.
A virtual round of applause. And okay, so that's it, everyone. So that's it for the day. And we'll be back tomorrow, starting at 11 a.m. Eastern time. And so I look forward to seeing you all tomorrow. So with that, I hope you enjoy the rest of your day, and we'll see you back tomorrow. Thanks.